A scalar quantity is a quantity with magnitude or size only. For example, distance. If I say to you, I'm walking a distance of 100 meters, then you know I've walked for 100 meters, but you don't know which direction I've walked in. A vector quantity, on the other hand, is a quantity that has both magnitude or size, and it also has direction. So that's like myself saying, I'm walking for 100 meters in due east. So now you know I've walked 100 meters, but in an easterly direction. So you know what direction I've gone also. So a vector quantity may be represented by an arrow. This is something that's really important. The length of the arrow represents the magnitude. The direction of the arrow represents the direction of the vector quantity. So an arrow that big shows that it's going towards the right, and it shows its size as well. A slightly bigger arrow shows that this force or distance or whatever it's representing is bigger than this one. So B is bigger than A, but it shows that they were going in the same direction. So here's some examples. This comes in foundation, but we should still be aware of everything. Mass, density, temperature, energy, distance, speed, these are all scalar quantities. Now, what I want to very quickly look at here is momentum. Momentum is mass times velocity. Mass is scalar, but velocity is a vector quantity. So automatically, momentum is a vector quantity. Acceleration equals the change in speed, in other words, v minus u, divided by time. Again, what is velocity? It is a vector quantity. Force, let's look at weight equals mass times gravity. What does gravity do to a person? It pulls them downwards. That pulling downwards automatically adds a direction as well. Displacement is similar to distance. Weight I've covered, but displacement is the same as distance, except it has a direction. So think back to the example I just gave 2 minutes ago. I went for a walk. I walked for 100 meters compared to I walked for 100 meters in an easterly direction. One was displacement. Me walking in an easterly direction, that's displacement. Displacement is the overall distance you moved from your starting point. So you could have walked 1,000 meters and then come back to your starting point, and your displacement will be 0. Okay, contact and non-contact. So first things first, what's a force? A force is a push or a pull that acts on an object due to an interaction with another object. So it could be myself closing the door. I could push it close. I could pull it open. It's my interaction with the door. So it's a vector quantity because you push in a certain direction, you pull in a certain direction. Now, if there's physical contact between the two, for example, in this case, my hand, oh, I need to learn how to draw, and the door handle, then that's contact force. So when there's physical touching, it's contact. When there's no physical touching, that is non-contact. For example, I've got a magnet here. I've got negative side, negative side. As I bring this magnet closer, what's going to happen to, as I bring magnet number 1 close to magnet number 2, what's going to happen to magnet number 2? It's going to move automatically. Do I have to make them touch? No. So that's a non-contact force. And just some examples of contact and non-contact. So contact would be friction, air resistance. Air resistance is a type of friction. Water resistance is also a type of friction. Anytime particles touch, it's friction. When you go for a swim, that's friction. When you go for a walk and you're walking through the air, that's friction. And one thing you need to always link this to is the energy that gets lost due to heat. So energy is lost due to friction. When friction occurs, two particles touch, then thermal energy is dissipated or lost to the surroundings. Then we've got tension. So that when you stretch a spring, and normal contact force, like pushing and pulling a door, opening something, closing something, pushing, kicking a ball. Then non-contact force, gravity, electromagnetic, and magnetic. And these are your three main non-contact forces. Okay, gravity. How do you work out the weight of someone? Weight equals mass times the gravitational field strength. Weight is measured in newtons because it's a force. Mass is measured in kilograms. And gravitational field strength is newtons per kilogram. Weight is the force acting on an object due to gravity. So when, in other words, it's gravity pulling down on particles. The amount of particles you have is the mass. When gravity pulls down on those particles, then we have weight. Now, gravity on Earth is 9.8 newtons per kilogram. If they don't give you that in the question, you can use 10 as well. But 9.8 will give you the more accurate answer. Now, if the question gives you a 10 for gravity, use the number 10. If it says 9.8, use 9.8. If it's on Mars or the Moon or Jupiter, it will give you a different number itself. So here's an example of a question. A book has a mass of 138 grams. Let's just remind ourselves, weight is in newtons, not kilonewtons, not meganewtons, not millinewtons or micronewtons, just newtons. And mass is in kilograms, not grams, not milligrams, not micrograms, not nanograms, grams. So we have to convert. If anyone's struggling to convert, if you go to the AMALearning website, YouTube channel, sorry, and you check out 1.3/1.4, there's a 2-3 minute video that's quite useful in helping in help that. So there's a 2 to 3 minute video that will help you understand how to convert from one unit to the other. So here we're converting from grams to kilograms. What do we do when we have grams to kilograms? We divide by 1000. That's why we've got 0.138 kilogram. Then we write down our formula. Substitute the values, and here it tells you that the gravity is 9.8. Do the maths, and we're looking for weight, so we need we want the units to be newtons, sorry. So it's 1.35 newtons. Now, generally speaking, in physics, 2 or 3 significant figures is sufficient. 2 decimal places, 3 significant figures, something like that is fine. And some question will ask for it to be in significant figures, so please don't miss those questions. Now, what is the resultant force and how are they calculated? So here we've got 1,000 Newton forward force on the engine, and notice this arrow here is bigger than this arrow here, which is what we understood when we were doing scalars and vectors, that a larger arrow represents a bigger force or a bigger vector quantity. The single force that could replace all the forces acting on an object is resultant force. Overall, if we do 1,000 Newtons, take away 750 Newtons, we get 250 Newtons in the left direction because that was the force that was bigger. That is now our resultant force. So rather than writing here 1,000 Newton forward force on the engine and 750 air resistance, we could get rid of all of that and just put one arrow and write resultant force. So if forces are acting in the same direction, you add them together. If forces are acting in the opposite directions, we subtract them, as we just saw. So here's just some practice questions that you can try in your own time and you can cover them up. But we'll just go through Let's go through this one and let's go through number 3 as well. So number 1 says, oops, sorry, a parachutist a parachutist has a weight of 70 newtons and an air resistance as they fall of 80 newtons. So what that means is when the parachutist is falling downwards, the weight is 70 newtons. The air resistance opposing that change is 18 newtons. Oops. So what is the resultant force? It's going to be 70 take away 18, which is 52 in a downward direction. So the overall answer is going to be 52 downwards. Now here in number 3, we say a car has a forward force of of 100 newtons. It has an air resistance of 22 newtons and friction between the car and the road is 32 newtons. So what we're going to do here is 100 and we're going to take away 22 and take away 32. Or you can put that in a bracket and add them first and then take it away. So we get 46 newtons and it will be resultant force of 46 in a forward direction. So not overly complicated, but still something we need to know. Okay, this definitely needs to be understood. You would draw a vector diagram. So how do we calculate the resultant force if forces are not acting on a straight line? So if forces are not acting on a straight line, how do we calculate the resultant force? What would we do? So you would draw a vector diagram to find the magnitude and direction of the force. So in this particular question, it's saying a skydiver jumps from an aeroplane. There is a resultant vertical force of 300 newtons. So because of the person's weight, they're dropping 300 newtons. So what you would do, you would say each one of these squares equals 60. Yeah. So let's do a little thing here so that we know. We're going to do our own version instead of what's on there already. 60 newtons. So we're saying downwards, the person's got a weight pulling them down by 300 newtons. And there's a horizontal force from the wind of 60 newtons. So what we've got to do, let's zoom into this a little bit more. We know our horizontal force is 60 newtons, so let's draw a line from here to here. Downwards for 300 newtons, we're going to have to draw for 5 boxes because 5 times 6 is 300. So 1, 2, 3, 4, and 5. So that's our 60, and there's our 300. Now what you do is you draw a line that starts from here all the way to here as a straight line. And you measure it. Now, let's say that box, we're not doing it as a box really, are we? We're doing it as a line. We're saying from there to there, that's 1 centimeter. And we're using 1 centimeter to represent 60 newtons. So now when you draw that line in between, the same line that's drawn here, just doing a different color. This same line, I'm just going to highlight it, this same line here, the same line I've tried to draw without a ruler, but it's kind of going all over the place there. If you measure that with a ruler now, you can times the number of centimeters by 60, and you've now got the resultant force. Because these forces are going in different angles, so you're going to get an average force of somewhere in between. So let's take this back to normal size. There we go. So you measure the length of this force using a ruler to determine the size of the force, which in this case is 304 to 308. They usually have a range just because everyone has, this a difference in interpreting data from a graph. Okay, work done and energy transfer. So what is work done? When a force causes an object to move through a distance, work is done on the object. So our force does work on an object when the force causes a displacement of the object. So work done is energy transferred by a force. So what that means is, let's just look at this in a bit more detail. Because essentially what it's saying is a force causes an object to move through a distance. So here's an object. We're going to move it from there to here. So along comes a person and they push. Now, when they push, what are they doing? They're exerting a force over a distance. Mhm. That's what work done equals. Work done equals the force exerted multiplied by the distance it's been exerted over. So work done is force times distance. Force we know is measured in newtons. Distance is measured in meters, so not centimeters. So how do we convert from meters to centimeters? We times by 100. How do we convert back? We divide by 100. And joules. Again, not kilojoules, not megajoules, not millijoules, just joules. So you've got to know, be ready to convert. Now, 1 joule of work is done when a force of 1 Newton causes a displacement of 1 meter. So that's why 1 joule is 1 Newton meter. So if we go back to this example here of the image I drew, let's say this person um, puts a force of 1 Newton and it makes it move by 1 meter here. We would say that that person has exerted himself with 1 joule of energy. So a joule is the same as a Newton meter. Work done against the frictional forces acting on an object will rise in temperature of the object. So like what I said before, what happens when particles collide with other particles? When particles collide with other particles, they transfer energy. So it causes energy to be lost, energy to be dissipated. So when we're doing work done is measured in joules. Potential energy is also measured in joules. Now, if I get a box and I increase its height by a certain amount, I've got a force exerted to lift the box and the distance that box has had to move. For that same scenario, if I've got a box, I have to make it move to a certain height. I've got a mass. I've had to overcome gravity and I've increased it by a certain height. Now, that potential energy is mass times gravity times height. Work done is force times distance. So these are interchangeable numbers. As in, if you know the energy it takes to lift that box, work done will be exactly the same. So you could get a question that says the energy required to lift a box was 900 joules. How much work was done? And you would say 900 joules. Now, the question after that might say, why is it that the numbers might not be exactly the same? And why might the numbers not be exactly the same? Because when work is done, you're going up against frictional forces, which means some of the energy is dissipated. So you might have 899, 880, 890. So in theory, potential energy and work done are the same, but you've got to keep in mind that with work done, frictional forces come into play. So some of the energy is lost to the surroundings. So that means the numbers are never exactly the same. But in a question, you will just put the same answer. Okay, work done and energy transfer. Again, if you applied, so just excuse me 1 second. If you applied a force to compress both a spring and a drinks can, what differences would there be and why do you think this is? So let's look at both. The spring is an example of an elastic object, meaning once you put force on it and you compress it, it goes back to its original shape. The can, on the other hand, is an example of an inelastic object, meaning if you apply a force, the can's going to crush, and once it crushes, it will permanently stay crushed. So that's inelastic. It won't go back to its original shape. So when a force is applied to either of these objects, they will change shape. Now, depending on the force applied, they may bend, stretch, or compress. A change of shape is known as deformation. So make sure you memorize that. Deformation is a change in shape. Both of these objects deform. The spring deforms because it coils up. But when you let go of it, the energy is released and it goes back to its original shape. With a soda can, it's inelastic. So when you add force, you deform it, but it's a permanent deforming. Okay, so elastic deformation is reversed when the force is removed. This means the spring will turn back to its original shape. Because when you push it down, what you're actually doing within the spring is storing elastic energy. And that opposes the force that was downwards. So it's almost like Newton's third law. You have a force that pushes downwards, you have a force that pushes back, equal in size, opposite direction. But inelastic deformation is not fully reversed. When the force is removed, this means, so when you remove the force, you push it down. When you remove that force, the can will not return to its original shape. Okay, so after 5.3, then the triple award top part will start. So anyone that's doing combined at that point can log off because we won't get through all of the triple content. We'll get through we will get through the triple content, but by the time we finish, there won't be any combined bit left. So this is the last combined part that we'll be doing for today. So below is a graph that shows the extension of a spring when a force is applied. What relationship does this graph show? So the line is straight. So initially we have a straight line and then it curves off at the end. So when it's a straight line, it shows proportionality. It shows direct proportionality. So look, the line is straight and it goes through the origin. That means it's directly proportional. The relationship is linear. And if we're going to describe this, as the force increases, the extension increases. But towards the end, the line begins to curve. At this point here, so from here to here, the relationship is no longer directly proportional, is no longer linear. That's the limit of proportionality right there. Limit of proportionality means the point at which Hooke's law is no longer obeyed or followed. And that is, so Hooke's law is the extension of a spring is directly proportional to the force applied. as long as the limit of proportionality is not exceeded. At the limit of proportionality, it actually, so let's use an example of a spring. We've got a spring. Its original size is this big. We add a weight to it. So now it extends to here. So we add another weight to it. So now it extends to here. So we add another weight to it. So it extends further. But at a certain point, what's going to happen? In a sense, the spring breaks. So we've all done this. We've taken a string and we've pulled it and pulled it. It goes back to its normal size. We pulled it a bit more, goes back to a normal size. Eventually, you pull it to a point where it no longer goes back to its original shape. Um, at that point, if you add more and more weight to it, the amount it stretches by becomes different. As in, we've reached the limit of proportionality when we get to that point, which is here in this graph. So the extent Hooke's law is the extension of a spring is directly proportional to the force applied as long as the limit of proportionality is not exceeded. So let's have a quick look at these questions. What is meant by elastic behavior? The object returns to its original shape when the force is removed. Now, during an experiment, the limit of proportionality was exceeded. What was this point? And give a reason for your choice. So look here, we've got a straight line. How do we know it's directly proportional? It's a straight line that goes through the origin. When it stops being a straight line, it is around, well, let's remove that line. You can actually see where it starts to curve. So let me do that line again. It starts curving, whoops, around this region here. Do that in yellow. So that yellow region is what we need to write down. So like it says here, between 5 and 5.8. And we know that's the limit of proportionality because prior to that, we can see proportionality between the force and the extension. That as the force increases, the extension increases, and they're directly proportional to each other. And we know it's directly proportional because it crosses the origin and it's a straight line up to that point. How can you tell from this graph below that limit of proportionality of the spring has not been exceeded? We can tell because the line is straight and it goes through the origin. Okay, forces and elasticity. So what's the equation that you would use to calculate extension of a spring? So force equals spring constant times extension. So there's your spring constant there. So you may have done direct proportion in maths. So for example, you might recognize this y equals kx. Now, if you know what y is and what x is, you can work out k. K equals y divided by x. It's a similar principle here. If you know f equals k times the extension, if you know the force and the extension, you can work out spring constant. Spring constant is just like the k in that you have in maths. It's just a constant that connects the force to the extension. So in this case, k would equal force divided by extension. Don't forget newtons for for force, and extension is in meters. So this question, a spring has a spring constant of 8 newtons per meter. Calculate the force needed to extend it 20 centimeters. Extension is in meters. Now, when you do your exam, you're going to be given every single formula, but you're not going to be told the units, not the correct units that you have to convert into. You need to know this one beforehand. So there's a lot of people going into physics at the moment thinking, I'm going to be given everything. It's not the case. You won't be given units. So first thing we do, divide this by 100. which is 0.2. Substitute in our numbers, 8 times 0.2, got 1.6. And add the unit, 1.6 newtons. Okay, how can you find the work done when a spring is stretched or compressed? So a force that stretches or compresses a spring does work. Elastic potential energy is stored in the spring. So a force that stretches or compresses a spring does work. Now, just so we can understand this, if this spring is initially this size, and then we compress it to this size, what have we done? We've applied a force, and also it's traveled a certain distance. And work done equals force times distance. So the spring, by compressing it, or even by stretching it, you have changed the distance it's moved. And you've done that by applying a force, so you can do the work done. A force that stretches or compresses a spring does work. Elastic potential energy is stored in the spring. So when we add that force to the spring, we are storing elastic potential energy within that spring. Provided the spring is not inelastically deformed, like the drink can that we saw before. So provided the spring is not inelastically deformed, the work done on the spring and the inelastic potential energy stored are equal. So if we multiply the force by the distance, we get work done. Work done and elastic energy always usually equal the same. Well, they equal the same amount. So elastic potential energy equals half times spring constant times E squared, which is extension squared. You will need to, a lot of the time you'll get questions. If you get questions on this, you'll need to convert units. So don't forget with meters and centimeters how to convert. Now, elastic potential energy is the energy stored when an object is stretched or compressed. So here's a quick example. A spring that has a spring constant of 1.2 newtons per meter is stretched 22 centimeters. So first things first, convert 22 centimeters into meters by dividing by 100. Substitute in our numbers, which is half times spring constant of 1.2 times 0.22. Multiply all together, we get 0.02904. Two significant figures is enough, so 0.029 joules of energy. Again, this is an important investigation that we have to be familiar with. And it is, of course, a required practical as well. Investigate the relationship between force and extension for a spring. So you set up the experiment as shown here. Adjust the ruler so that the 0 mark is the same height, is at the same height as the top of the spring. Or I would not say top of the spring, I would say bottom of the spring. So you want the ruler, if this is your spring, you want your ruler on level there. So when it stretches, you again measure the bottom of the spring. Now you record the length of the spring when no weights are attached. So it might be, for example, 5 centimeters. So you've added no weight, 0 newtons. Then you hook a 1 Newton weight on the bottom of the spring and record the new length of the spring. So it could be 7.5 centimeters. Then you add another Newton weight and it might be 10 centimeters. Then you might add a third Newton weight and it might be 12.5 centimeters. You add weights at 1 Newton intervals recording the new length of the spring. Determine the extension of the spring when each weight is added by subtracting the original length from the recorded length. So you already know what your original length is. When it stretches, you measure that new length. Now you've got force and you have extension. So you can draw a graph to show the proportionality, the relationship between the two. Okay. If anyone's doing combined, you can log off at this point. Thank you. And because the remainder of this session will now be triple award. So, what are moments? A moment is a turning effect of a force. So, but it's important because this is usually taught in schools, the word turning effect. But if you ask a student, what do we mean by turning effect? Not many students can actually answer the question. And it's not a question that will necessarily come up in your exam, but it is important that you know what the term means. So the turning effect means how much a force tries to make something rotate around a point. For example, opening a door. So imagine if you look at a door from above, it's hinged on to the wall. So this is the hinge where it touches the wall, and this part here is the door. If I exert a force, what's going to happen? It's going to spin around that hinge. So that's what we mean by turning force. How much a force tries to make something rotate around a point. Now you can call that point a pivot or a fulcrum. We in England generally call it a pivot. But I've seen the word fulcrum used as well. So when you push a door, you're applying a force. The hinges are the pivot. The hinges are the pivot. The further from the hinges you push, the easier it's to turn the door. So now what we're saying is, here's your hinge, here's your door. If you push it from here, it's going to take more force because the distance from the pivot to the hand is less. If you push from here, it's going to be easier because the distance from the pivot to the hand is more. So when you're working out moments, it's force times distance, as in the distance from the pivot to the point where the force is applied. So the distance we call a multiplier. So the bigger the distance, the less force needs to be applied. So moment of a force equals force times distance. Again, don't forget meters. So levers. Levers are a simple machine consisting of a pivot. There's the pivot, an effort and a load. So in this case, the effort is downwards, so we have a force. Now, the moment is the movement of the stick in this case in an anti-clockwise direction. I'll show you what I mean by that. So when we apply a force, our moment will go this way in an anti-clockwise direction. The size of the moment will be the distance from the pivot to where a person's pushing down from. So it could be a person stands here to try and remove that rock. So whatever the force of that person downwards multiplied by the distance from the pivot is the force that's going to be applied to this rock, this load. And that means this part here that's underneath the rock will also move anti-clockwise to move it out of the way. Okay, let's use gears as an example. So gears are toothed wheels used with other axles at different speeds. So gears, I added this extra information in just so you can read it as well and just understand it properly. So gears are wheels with teeth that fit together, as we can see here, the picture at the top. When one gear turns, it makes another gear turn. And this happens because of moments and turning forces. Now I'm going to read this out, but then I will explain it using the picture at the top. Force is applied to one gear called the driver gear. So this, you don't need to know this terminology, but this is the driver gear. This whole thing. This is the driver gear. Now, this force creates a moment, a turning effect about its center. The teeth of the driver gear push on the teeth of the next gear. So what that means is this. Let me just remove this, use a different color. From that middle point there to this part here where the end of the tooth is, that's the distance. Now, if someone exerts a force, for example, from there, in that case, the distance would be to there, from the middle. So we would do force times distance, and we have our moment. What that means now is that this wheel is going to spin around this way. So we have a clockwise moment. Now, when that moment, when this part of the tooth hits this part of the tooth here, this cog will in the opposite direction. So it'll have an anti-clockwise moment. It will be equal in size though. But the difference now is the distance between the two, the distance from the tooth part and the middle is less. The moment is the same, but the distance is less. What does that mean? That means the force will be bigger. So now we have a bigger force going through this cog. So the force is applied to one gear called the driver gear. This force creates a moment about its center. The teeth of the driver gear push on the teeth of the next gear, transferring the moment. This causes the driven gear, so this is the driven gear. Again, you don't need to know the term to rotate. But if the driven gear is larger, it turns more slowly, but with a bigger force. If the driven gear is smaller, it turns faster, but with less force. Okay, pressure in a fluid. The pressure in fluids causes a force normal, in other words, at right angles to any surface. So pressure equals force normal to the surface area of that surface divided by area. So pressure equals force divided by area. Pressure can be measured in pascals, force in newtons, and area is meters squared. Another one that you need to keep in mind is pressure equals the height times the density of the liquid times gravitational field strength. So HPG. Height in meters, so always convert from centimeters to meters. We've got density, which is kilograms per meters cubed, and gravitational field strength, which is newtons per kilogram. Again, both these formulas, you're going to be given them as they are, but just make sure you know the units. Okay, pressures in a fluid. Part 2. What causes upthrust? Sorry, excuse me 1 second. So what causes upthrust? Is that a partially or a totally submerged object experiences a greater pressure on the bottom surface than on the top surface. This creates a resultant force upwards, and this force is called upthrust. So when something is being forced downwards, then as it moves down, all the water particles that it's going past are pushing it back upwards. Opposite direction but equal in size. So that causes an upthrust. So what is the atmosphere? The atmosphere is a thin layer relative to the size of the Earth of air around the Earth. So the atmosphere is a thin layer of air around the Earth. And when we say a thin layer, we're saying relative to the size of the Earth. So the Earth is a lot bigger than this thin layer. But the thin layer, if you compare it to other things, would, I suppose, be classed as something that's big. The atmosphere gets less dense with increasing altitude. So the higher up we are, the thinner the air. So air molecules colliding with a surface create atmospheric pressure. So you have when air particles collide with something, that's pressure. But as you go higher up, the pressure decreases because you've got less particles. You've got more particles towards the bottom. So what is the atmosphere? It's the number of air molecules, in other words, the weight of the air, above the surface, and that decreases as the height of the surface above ground level increases. So as you go higher up, you have less air particles. So as the height increases, there's always less air above a surface than there is at a lower height. So the lower down you are, you've got more particles adding pressure. When you're higher up, you've got less particles, less pressure. So the atmospheric pressure decreases with an increase in height. 5.6.1.1, which is distance and displacement. So what are distance and displacement? So this is something we've already covered. Distance is how far an object moves, which is scalar. Displacement is the distance an object moves, measured in a straight line from the start point to the finish point. So that's a vector. So it gives us a direction as well. Speed is a measure of how fast an object is moving, and the speed of and velocity is the speed of an object, but with a given direction. So that's vector. Now here's some typical values for speed. It is something that needs to be covered from a curriculum perspective, being able to estimate, have an understanding of, and it sometimes comes up as a 1 mark question. I've seen it more in foundation papers that walking is around 1.5 meters per second, running is 3 meters per second, cycling 6 meters per second. You do definitely need to know this. The sound in air is 330 meters per second. And, and obviously an understanding that these are never constant. Each person will have a different value and we go faster and slower at different points. Okay, how do we calculate speed? So you will be given this formula in your formula booklet, but distance traveled equals speed times time, or speed equals distance divided by time. So let's have a quick practice question. The distance someone will travel, calculate the distance someone will travel if they're moving at 1.5 meters per second for 1 minute. So if they're traveling 1.5 meters per second for 1 minute, first thing we've got to do is convert the 1 minute into 60 seconds. So these questions always come across straightforward, but lots of students always miss that mark because they forget to convert. So the distance equals speed times time, so 1.5 times 60. So it means in 1 minute, this individual would have traveled 90 meters. So what happens to velocity and speed during circular motion? So planets orbiting the sun are an example of circular motion because the planets are going around in a circle, but close to a circle. The planets have a constant speed in their orbit because the gravity that's pulling them towards the sun doesn't change, the speed is going to stay the same. However, the velocity of the planets is constantly changing, and that's because they constantly change direction. So don't forget that when we say something's scalar, it means it only has magnitude and size. So the size of the speed stays the same. However, when we look at velocity, velocity is a vector. It's size plus distance direction. So it's magnitude and direction. So here, when we're talking about velocity, the size, or as in the speed stays the same, but the direction is constantly changing because it's going around in a circle. In other words, the velocity is changing. Now, what is change in velocity divided by time? It's acceleration. So in that respect, the planet is accelerating around um, the sun, even though the speed doesn't change. It's because the direction is changing. So the velocity is not constant. It's constantly changing. Okay, distance time graphs. Important to understand what each thing represents. So if you've got a constant straight line like this, that means it's moving at a constant speed. Now, if you compare number one to number two, they're both constant speeds, but this one has a steeper gradient. So I could just draw it here. The one with the steeper gradient is moving faster. And if the line is just a flat straight line, that means the distance isn't changing. That means the person has stopped. So if we look at this graph here, between A and B, the person is traveling at constant speed. From B to C, it's still constant speed, but the person is moving faster. And then back from C to D, the person is moving at constant speed, but again, they're moving slower again. Now, if you need to find the speed between 2 points, all you do is work out the gradient. So in a distance time graph, to find out the speed that the person was traveling at, you work out the gradient. So let's try that. Let's zoom in and let's do, sorry, let me zoom out. Let's do section A to B. So the gradient is the change in Y So what's our change in Y? That's 100. So our change in Y equals 100. And what's our change in X? It's 3. So speed will equal 100 divided by 3. In other words, 33 meters per second, or 33.3 recurring meters per second. The example they've given is from B to C, where the change in Y is 250 and the change in the x-axis is 4. So 250 divided by 4 is 62.5. Now, that C to D is the same as A to B. So we've already calculated this, 33.3 meters per second. Okay, how do you calculate acceleration? Acceleration equals the change in speed. Change in speed is the final speed minus the initial speed divided by time. And acceleration is measured in meters per second squared. So how do we work out the acceleration? Now we're looking at a velocity time graph. So in a velocity time graph, you can work out the acceleration by working out the gradient of the line. So here you can see the change in the y-axis is 18, the change in the x-axis is 6. So it's just 18 divided by 6. And when you're using a velocity time graph, how do you know how far someone has traveled? How do you know how far someone's traveled? We know because of the area under the graph. So you just have to use either you work out the area of a trapezium, which is half times that's these two lengths, the two lengths which are that are parallel to each other, times the height, as in the distance between A and B. Or you can split it up into two triangles and a rectangle in the middle. Whatever works best for you. Okay, what is uniform acceleration? So this is another formula. You will be given it um, in your formula booklet. But when we go through the numeracy part of the pre-exam workshop, we're going to be doing a lot of practice on these kind of formulas. So final velocity squared minus the initial velocity squared equals 2 times acceleration times the distance. And again, as I always say, you've got to know the units well. Okay, what is acceleration when an object falls under gravity? What this means is if that individual is falling from a plane, what's causing them to accelerate? The thing that's causing them to accelerate is gravity. Gravity pulls them down at 9.8 meters per second squared. What that means is it's causing that. Let's use 10 just to make it easier. What that means is after 1 second, gravity will take that person's speed from 0 to 10 meters per second. After another second, it will increase it because acceleration means how much it's increasing the velocity by every single second. So if I said something is 2 meters per second squared, it means someone's speed is going from 2 to 4 to 6 to 8 to 10 to 12. It's increasing by 2 each time. So gravity makes the person's acceleration increase by 9.8 each time, but I'm using 10 for ease. So after 2 seconds, it's 20 meters per second. After 3 seconds, it's 30 meters per second. Until that force that's pulling the person down is balanced out by air resistance. When air resistance equals is equal to the force pulling the person down, then the speed can no longer increase. Because to increase the speed, there needs to be a force, a bigger force in one direction. So eventually the resultant force will be zero. So when the air resistance is equal to gravity, at that point, or the gravitational force, at that point, the resultant force is zero and the object moves at terminal velocity. Terminal velocity being the maximum speed that that object can move at. Okay, Newton's first law. If the resultant force acting on an object is zero and the object is moving or the object is stationary. So if the resultant force acting on an object is zero, one of these two scenarios is happening. The object is moving or the object is stationary. Now, let's look at each one separately. If you've got a table, you've got an object on top of that table. The downward force is counteracted by the upward force from the table. So the resultant force equals 0 newtons. That object isn't going to move, it's stationary. Now let's look at a car. Let's look at a few different scenarios. Let's look at car number one. If car number one has a bigger force this way and a smaller force this way, what will happen to that car? It's going to accelerate in that direction. If you've got another car and it's got a bigger force going that way than this way, then that car is going to slow down. It's going to de-accelerate. Now, if you've got the final scenario car where the force going forward is balanced out by the air resistance, then that car is going to move at constant velocity. The thing here is that it's not going to accelerate, it's not going to de-accelerate, but whatever speed it's moving at, it's going to constantly just move at that speed. That's constant speed. So when the resultant force acting on an object is zero, the car is either moving at constant speed, constant velocity, or the object is stationary. Okay, so what is inertia? Inertia is the tendency of objects to continue in the state of rest or uniform motion, meaning how likely they are to continue moving. Now, Newton's second law is force equals mass times acceleration. So this is resultant force equals mass times acceleration. This is a law of motion that states the acceleration of an object is proportional to the resultant force acting on the object and inversely proportional to the mass. So what that means is if we increase the force of something, we increase the acceleration. So this is what we're saying with the car. The only way that car is going to move forward is if we increase the forward force. Then the car will accelerate. So inertial mass is a measure of how difficult it is to change the velocity of an object. It's defined as the ratio of force over acceleration. Okay, now this is a required practical. It's important that we fully understand this practical. And it's something that commonly comes up in questions. So it's something that we'll cover in a lot more detail in the pre-exam workshop. So how can you investigate the effect of varying the force on the acceleration of an object? So set up the equipment as shown here. You got your trolley. It's attached to this pulley, which is attached to a weight. You've got two light gates. Usually add a piece of card just there. So when it goes through the light gate, it triggers the light gate. And the light gate is attached to a data logger. So just like a computer screen, in other words. Now, when it passes through the first light, it measures the speed at which it's traveling. So you've got initial speed. But when it goes to the second light gate, it measures the final speed. And it measures the time between. If you've got initial speed, final speed, and time, v minus u divided by t, what does that equal? Acceleration. And that depends on the force that's applied here. So you do that for 1 Newton. Then you add another weight to it. So you do it for 2 Newtons. Do the same thing for 3 Newtons, 4 Newtons. And you make sure you do the experiment multiple times. So you do the experiment 3 times, you get rid of anomalous data, and you average your results. So it says here, set up the equipment as shown in the diagram, connect the two light loggers to a data logger, add 1 Newton of weight to the pulley. That is the pulley. And release the trolley. Light gates A and B will determine the velocity at each point. So we've got initial and final velocity, and we can use this to calculate the acceleration between the 2 points. So record the acceleration when 1 Newton is added, then you repeat the whole experiment by adding more weights at 1 Newton intervals. So we do the whole thing again, with 2 newtons, 3 newtons, 4 newtons, 5 newtons. But of course, what do we need to do? Alongside this, we need to repeat the experiment 3 times and get an average. 5.6.2.3 Newton's third law. So this is a law of motion that states that whenever two objects interact, the forces they exert on each other are equal in size but opposite in direction. So what that means is this ball pulls down on this spring. It has a downward force. So and let's say the force is 10 newtons. The spring then exerts a force in the opposite direction, but it's still going to be equal in size. So these forces are equal in size but opposite in direction. That's all Newton's third law is. So for example, you have two people and they're leaning against each other, as in just from their hands. They push their hands against each other, but they don't move. What that means is person one's hand exerts a force in this direction, and person two exerts a force in the opposite direction. They're equal in size because they're not moving. They're in one place, but they're opposite in direction. So the forces are equal in size but opposite in direction. So every time you exert a force on something, that object exerts a force back, equal in size, opposite in direction. So that's how a rocket ship works. The force from the bottom of that looks like an upside down candle, but it should be a rocket ship. So you've got the force from the flame going downwards, and then you have the opposite force, which is equal in size but opposite direction, that makes the rocket ship then actually move upwards. Okay, again, another very important question, another important topic that when we do our pre-exam workshop, or more importantly, when you're doing your own past paper practice, you're going to see lots and lots of this. So, what is stopping distance? So, for a given braking force, the greater the speed of the vehicle, the greater the stopping distance. So, the faster a car is going, the longer it's going to take for a car to stop. Now, if we see, for example, someone's driving a car, you're riding a bike, it's on the bike, and all of a sudden, a cat jumps in front of you. What do we have to do to stop? Number one, we have to think. There's the time is the distance your bike will travel while you're thinking about what's just happened. So your brain is processing the information. It then sends a message to your hand, and then your hand pushes down on the brake and you stop. Now, if you're going really, really fast, it's going to take longer for you to stop. If you're going slightly slower, it'll take less time for you to stop. The thinking distance is always roughly the same, unless there are things that can cause distraction. Braking distance depends on how fast we're going. It can depend on a few other things as well. But stopping distance is when you add both of these things together, the thinking distance and the braking distance. So a driver's reaction time can be affected by, now typically our reaction time is 0.2 to 0.9 seconds, but it can be affected by tiredness, drugs, alcohol, and distractions such as phones, iPads, anything. The braking distance of a vehicle can be affected by poor road conditions or weather conditions, so like wet and icy roads. It could be the poor condition of the vehicle. It could be that the tires are worn out, the brakes are worn out. So when you put your foot on the brake, it takes a while for it to kick in. Now, the braking distance of a vehicle will be affected by the greater the speed of the vehicle, the greater the overall braking distance needed to stop the vehicle in a certain distance. Meaning the faster we're going, the further that car is going to go before it stops. The greater the braking force, the greater the deceleration of the vehicle. So the better the brakes are working, the quicker you're going to be able to deaccelerate. Larger deaccelerations may lead to brakes overheating and or loss of control. So if a car's going really, really fast, this goes back to friction. When you push down the brakes, you've got pads that come in contact with each other, and that's friction. So the person's going, the more likely they're going to overheat, and the more likely that the car can skid or lose control. Okay, momentum. Now, momentum is the last part of topic 5, and it's all higher tier. So this initial part is higher tier. Um, yeah, all of momentum is higher tier. We're going to go through momentum as a property of moving objects, conservation of momentum, and then finally changes in momentum. Now, 5.7.3 is changes in momentum, and that's physics only. And then after that, so that'll be a 5 minute wait, a few minute wait for whoever's doing combined, and then we're going to move on to topic 6. Okay, so a vector quantity. So momentum is a vector quantity, and it is the product of mass times velocity. Again, don't forget your units, kilograms for mass. So let's have a quick look at this question. A toy has a mass of 150 grams. How do we convert grams to kilograms? We divide by 1000. You then write down the formula, substitute the values. Mass is 0.15, velocity is 0.08. So our answer is 0.012 kilogram meters per second. Okay, 5.7.2, conservation of momentum. What happens to momentum in the event of a collision? So as long as the system's closed, meaning energy is not lost from that system, particles aren't lost from that system, the total momentum before an event is equal to the total momentum after the event. For example, if two cars with equal momentum were traveling in opposite directions, overall the momentum will be 0 kilogram meters per second. So let's just look at that in a bit more detail. You've got car A and you've got car B. They're exactly the same car, so they have exactly the same mass. So let's say car A has a mass of 1000 kilograms. No, let's put 100 kilograms. Let's keep it easy. It's traveling at 10 meters per second. Now B is identical car, so it also weighs 100 kilograms. Cars don't weigh 100 kilograms, by the way. More usually in the tons, so 1000 kilograms and above. And its speed is also 10 meters per second. Now, I made one mistake here. Can anyone tell me what that mistake is? Because velocity is a vector. So what should I have put for my velocity for B? Is it accurate for me to have written 10 meters per second for A and 10 meters per second for B? Is that accurate? No, it's not accurate because this is a vector. So this is plus 10 meters per second and this is minus 10 meters per second. Now, when these cars collide with each other, what's the momentum of A? The momentum of A, so it's mass times velocity, 100 times 10 is plus 1000 kilogram meters per second. The momentum of B is minus um, 1000 kilogram meters per second. So before they even collide with each other, so total momentum before is going to be 1000, take away 1000. So it's going to be 0 kilograms kilogram meters per second. Now, when they collide, because they have the same momentum, their velocities and their masses cancel out. So when they crash, A and B don't move, they're stationary. So if they're stationary, momentum equals mass times velocity. Our velocity is 0. So we've got 200 times 0. So what's our total momentum after the event? Is also 0 kilogram meters per second. So that means momentum has been conserved. Momentum before the event, before the crash, was 0. Momentum after the crash was also 0. So what would happen when a standing ice skater throws a bag forward? Well, the bag will now have forward momentum. So we're talking about a standing ice skater. The ice skater's got skates on. Well, I don't know how to draw skates, never mind. So this person's got skates on and they throw a bag forward. So I know that shows a rock, but let's just assume the rock's inside a bag. The bag will now have forward momentum and the skater will move backwards. So momentum before the bag is thrown is 0. Momentum after the bag is thrown is also 0 because the bag will have positive momentum because it's moving forward and the skater will have negative momentum because it's moving backwards. So when we do mass times velocity for the skater, it will be negative, and for the bag, it will be positive, and they will cancel out to equal 0. Predict what would happen if a car crashes into the back of a stationary car. So the stationary car moves forward after the collision. So we've got two cars. This car goes into the back of that car. Now, this is before the crash and after the crash. After the crash, they're both going to move, but this car number one isn't going to be moving as fast as it was before. So, before the collision, one car has momentum and the other doesn't. So, one has momentum, whatever that is, the other car doesn't, so that means its momentum equals 0. The car that crashed will also move forwards, but at a slower speed as it has less momentum. Momentum before the collision is the same after the collision due to the conservation of momentum. So if we worked out the momentum of car 1 and car 2, it would equal to whatever the momentum of car 1 was initially. I'm not adding 2 there because the momentum of car 2 we know would be 0 because it's not moving. Okay, 5.7.3. So this is just a few slides and this is triple only. When does a change in momentum actually occur? And what we need to know with this is how momentum and understanding how momentum works keeps us safe in cars with things like airbags and seat belts. So a change in momentum occurs when a force acts on an object that is moving or is able to move. So a change in momentum occurs when a force acts on an object that is moving or is able to move. So force equals change in momentum divided by change in time. So the way you could look at this is change in momentum is momentum before and momentum after. So force equals momentum after minus momentum before. So momentum equals mass times velocity. That's the final velocity Take away from that mass times the initial velocity and divide that by change in time. So if we can increase the time it takes for something to occur, what do we automatically do? We decrease the force. That's why some cars have crumple zones. So this is coming up anyway, or it should be coming up in the text. Crumple zone is where when a car actually bumps into something, the front part of the car crumples up. What that actually does is it increases the time it takes before the crash occurs. So you can imagine if a car, front of a car, bumps into a wall, as soon as it collides into the wall, you got a force. And it's the change in momentum divided by time. So whatever that car was going at is the initial momentum until it stops. And the time taken for it to stop and for that crash to complete is going to be really quick. Now here, you have an initial momentum. The final momentum will still be zero because the car is going to eventually stop because it's collided with a wall or whatever it is. But now, before it actually crashes, what will happen is this front bit crumples. So because it's crumpled up, it takes a little bit longer till the car actually stops, and that increases the time taken. Therefore, the force is less. So let's have a quick look at this question here. Now, this question already gives most of the points. You don't not much working out to be done here. A cricket ball has a change in momentum of 9.6. So let's substitute that in. Divided by over 1.1, sorry, 1 millisecond. Now, how do we convert milliseconds into seconds? We divide by 1000. So we're doing 9.6 divided by 0.001. So the cricket ball is struck with a force of 9,600 newtons. Okay, how do safety features such as a crash helmet actually work? The helmet has a lining which is designed to crush in the event of an impact. So the head is actually here, but within there, before a collision occurs with the head, you have a section here that is designed to crush before it hits the head. Now, because it's designed to crush, this increases the time taken for the head's momentum to reach zero. So force equals change in momentum, which isn't necessarily going to change, divided by change in time. So if we increase the time taken, what have we done? We've decreased the force because they're inversely proportional. That reduces the forces acting on the head, and so it prevents injury. So very important safety feature. All of these safety features do exactly the same thing. With an airbag, as soon as the head collides, before it hits the steering wheel, which is here, it takes longer because it has to go through that bag of air before it collides with the steering wheel. So again, we've increased the time. Gym mats, because they compress, so it takes longer before you actually collide with the ground. So less force. Seat belts. Seat belts. Seat belts. So if someone's driving at like an extreme speed and they've got the seatbelt on, what the seatbelt does is it means it takes longer for that person's head to collide with the windscreen because keeps them back. Again, time's been increased. Same with playground floors. It's this kind of soft AstroTurf type thing. Kind of sorry, not AstroTurf, like a soft, yeah, yeah, soft spongy material, and that means if a child falls on it, it compresses before the child stops. So it takes longer for them to reach a momentum of zero. So again, force is decreased. Okay, that's the end of topic 5. So we're now going to start topic 6. Okay, we're continuing with topic 6, waves, which is physics AQA paper 2. So transverse and longitudinal waves. So an example of a transverse wave is a ripple on the surface of water, and sound waves are examples of longitudinal waves. Transverse waves do not have areas of compression and rarefaction. Longitudinal waves do have areas of compression and rarefaction. A transverse wave, the vibrations of the particles are at right angles to the direction of the wave. So here we've got the energy moving this way, because a wave is a transfer of energy, it's the movement of energy. But as it goes through particles, the particles move up and down, but the particles itself don't move from left to right, as in they're not transferring the energy from one place to another. So if the sun releases a transverse wave, because that's what sunlight is, as it's going through things, so the energy is going this way, it'll cause particles, disturbance within the particles will move up and down at right angles, but it's not actually carrying the energy from the sun. Now, in sound waves, you get areas of rarefaction and compression. Compression are the areas where there's lots of energy, and rarefaction is the gaps in between. So compressions occur when a person's talking. Now, it means when a person starts talking, the wave energy travels. So, for example, from someone's mouth here to someone's ear here. The sound is moving across. Now, the energy goes into a particle. The particle starts vibrating parallel. So the oscillations are parallel to the direction of the wave, but it's not the particles itself that are carrying the energy. Otherwise, that would mean every time we speak to someone, it's that person's breath that's entering our ear, which is not the case, because the particles vibrate back and forth. When they've got more energy, they vibrate faster. They transfer their energy from particle to particle to particle until it reaches our ear and it vibrates our eardrum. So how can we prove that it is the wave traveling and not the air or the water itself? So one example is if you place a floating object such as a rubber duck on the surface of water, you just cause a small disturbance. You'll observe the duck moving up and down, and as the wave passes, so the small disturbance, you'll see the wave moving through, and you'll see it moving back, but you'll only see the duck moving up and down. You won't see the duck flowing with the water back and forth. Okay, so we need to be able to label transverse uh, transverse waves and understand what each thing means. So first thing is wavelength. Wavelength is when you go from one peak to another peak, a crest to a crest, or from anywhere, any point to a corresponding point. So it could be from here to here. That's a wavelength. So a wavelength is just the length of one wave. You could go from here to here. That's a wavelength as well. Then we've got amplitude. Amplitude is the maximum displacement of a point on a wave away from its undisturbed position. So its undisturbed position is here, this line. So the maximum position it moves up to is there. So that would be this wave's amplitude. Crest is the top of the wave and trough is the bottom of the wave. Now, frequency. Frequency is the number of waves that pass each point per second. So we look here, if this was 1 second, then here we'd have 1, 2, 3 waves. So the frequency would be 3 hertz. How do we find out how long it takes for one wave to occur? You just do 1 second divided by the frequency. So in this case here, we do 1 divided by 3. So each wave lasted for a third of a second. So wave speed. This is the speed at which the energy is transferred through a medium. So the speed at which the energy is transferred through a medium. So light and sound change speed as they go through different densities. So wave speed equals frequency times wavelength. Again, don't forget wave speed. Wave speed is actually meters per second. Wavelength meters and frequencies in hertz. So make sure your meters is always measured in. Wavelength is always measured in meters. Okay, how can we measure the speed of sound waves in air? So one thing you can do is get two people to stand 500 meters apart. One person fires a gun into the air and raises their hand into the air at the same time. So they've got their gun and they stick their hand up at the same time. Now the second person records how long it takes for them to hear the bang. So they've got a stopwatch and they click on the stopwatch as soon as they hear the bang sound. Sorry, as soon as they see the hand. So as soon as they see the hand, they click on the stopwatch. As soon as they hear the sound, they click it again. And that gives a time. And speed equals distance divided by time. The biggest issue here is that people have a reaction time of 0.2 to 0.9 seconds. So whatever that time is give or take 0.2 to 0.9. So it's a significant give or take. So 6.13, 6.14, and 6.15 are all triple award. Now, waves can either transmit, absorb, or reflect. So when a wave passes through a material, that's transmitting. When a wave is taken into a material, that's absorption. Absorbing, and reflect is when a wave changes direction at a boundary and remains in the incident medium. So if we're going, for example, from the air and this was glass, the boundary is the line in between the two different mediums. So reflection of waves. We've got our incident ray, a reflected ray, and our normal. The normal is always at 90 degrees to the boundary line. So here's our boundary line between the air and the glass and the mirror. The angle of incidence always equals the angle of reflection. Now, quick practice question here. The diagram shows what happens to the energy transferred by a ray of light. Calculate the percentage of the energy absorbed by the glass block. So we've got 8% that's been reflected, 90% that's gone through the glass and has been refracted. So the amount that's been absorbed is whatever's left, which is 2%. Okay. So how can we investigate the reflection of light by different types of materials? So place a block on a piece of paper and draw around it, usually with a piece of paper with a pencil. Shine a ray of light through the block or towards the block. Mark the ray of light close to the point it leaves the ray box and where it hits the block. So just where it leaves, you put your first cross, and where it hits the block, you put your second cross. And then same thing with the reflected part, you draw your cross. Now you can move your piece of glass out of the way, and with the ruler you can join the crosses. Now the only thing you need to do is the point where the reflections occurred, you draw a normal line which is perpendicular, so at 90 degrees to the surface, as into to the boundary. Using a protractor, you calculate angle of reflection, well, your angle of incidence and your angle of reflection. Now you shine the light from the ray box at different angles, and you increase the angle of incidence by 10 degrees each time. Now, what you should get is that the angle of incidence and reflection are exactly the same at each point. Now, how can random errors occur when investigating reflection? So if you're struggling to determine the center point of the ray, that's one reason why. Not putting the mirror back in the right place after taking some measurements, and random errors can lead to uncertainty. Now, what is uncertainty? The interval within which the true value of a quantity can be expected to lie is determined by finding the range of data. So the uncertainty is finding the range of data and dividing by 2. So for example, here's a set of data. The range, it goes from 48 minimum, 60 at the max. The range is 12. So we divide that by 2. So uncertainty is plus or minus 6 centimeters. Here the range is only 7, so divided by 2, so the range is plus or minus 3.5. Here the range is only 1 centimeter, it's between 21 and 22, so the range is 1 centimeter, so half that, and the range is, give or take, half a centimeter. So now the table below shows some results obtained when the ray of light was shone on a mirror. For each angle of incidence, the angle of reflection has a range of values. This is caused by an error. What type of error will have caused each angle of reflection to have a range of values? Because the angle of incidence should equal the angle of reflection. So why do we have a difference? And why do we have a range? Suggest what the student may have done incorrectly during the investigation to cause each angle of reflection to have a range. So number one, not place the mirror or the ray box back in the same place, or misjudging the center of the ray. Okay, now we're looking at refraction. How can we investigate the refraction of light by different types of materials? So essentially, it's the same process. Draw your crosses. Initially, draw around your glass block. Shine your ray of light. Draw your cross where the as close as you can to the ray box, as close as you can to the glass. Now this time, where the light exits from, you draw a cross and a bit further on. So now we've got 4 lines to draw a line, 4 crosses to draw a line through. So you've got your initial line, your refracted line, and then your emerging line. And then again, where you've got your boundaries, you draw your normal lines at 90 degrees. Using a protractor, you measure the angle of incidence and the angle of refraction. Now in this case, and then you change your angle of incidence by 10 degrees each time. So you get a range of angle of incidences, and you see the impact that has on the refraction. The angle of refraction should be smaller. Okay, so here's an exam practice question. Describe a method the student could have used to obtain the results shown in the graph. So number one, place a glass block on a piece of paper. So exactly what we went through before. Draw around the block, shine a ray of light through the glass block, mark the ray entering and emerging from the block. Also, you should also mark the point where the light originates from. Join the points to show the path of the ray. Draw a normal line at 90 degrees to the surface. Use a protractor to measure the angle of reflection and incidence. This could also be to measure the refraction and incidence. And repeat, increase the angle of incidence in 10-degree intervals. So exactly what we went through. So this is a really good method to memorize for reflection or refraction. Now explain why using a wider ray would give less accurate results than using a narrow ray. So this is from the ray box. So when the light comes out the ray box, you've probably done this yourself. You put this thing in front of it that has that makes the light come out in lines. So if the narrower you make those rays of light, the more accurate it is. That's because it's hard to judge where the center of the ray is if the ray of light's wider, and that leads to a bigger uncertainty. Now here it says calculate the uncertainty. So what do we need to do? Find out the range. We've got 3 bits of data here, 28, 25, 22. So the range is 6. Divide that by 2, and our uncertainty is plus or minus 3 degrees. Okay, 6.14, 6.1.4, sound waves. This is again a triple only topic. So this is physics only. Sound waves can travel through solids. Sound waves can travel through solids, causing vibrations in the solid. So sound waves can travel through solids, causing vibration in the solid. Within the ear, sound waves cause the eardrum and other parts to vibrate, which causes the sensation of sound. The conversion of sound waves to vibrations of solids works over a limited frequency range. So we can only hear between 20 hertz and 20,000 hertz. So what we're saying here, let's start with this first bit. A solid is made up of particles. I'll do the particle slightly bigger to save time. Now what will happen is when energy is absorbed by the first particle, it vibrates and it passes energy onto the next particle, which starts vibrating. Pass it on to next particle, next particle, next particle. Our ear works in a similar way. Our eardrum, when these, so when we're talking to someone, when the particles travel through the air, when the sound waves travel through the air. So sound waves are longitudinal waves. They cause the particles to vibrate or oscillate parallel to the direction of the energy. When the energy reaches the air that's within the ear, they hit the eardrum. And then within this part of the ear, the cochlea, that's full of water. So you've got this part of the ear here, which are tiny bones, and those tiny bones magnify the vibrations. And when it enters this water part here, there's tiny hair-like receptors within that water. So the cochlea is full of water, and it's these tiny hair-like projections, which are receptors. When they vibrate, they send the message to the auditory nerve, which is a sensory neuron, and it sends it to the brain. The brain then interprets those vibrations. Well, the interprets the electrical impulse which arrives through the auditory nerve as a sound. But our ears can only handle 20 to 20,000 hertz. That means 20 vibrations or oscillations per second to 20,000. So if our eardrum is hit by something less than 20 times, we don't detect it. So for example, air particles. Air particles are constantly hitting our ear. We don't register it as a sound. Otherwise, we'd hear this beating of the air all the time. And anything above 20,000, for example, a dog whistle. A dog whistle works at over 20,000, 20, 22, 23, 24, 25,000 hertz. It would hurt our ear because it's causing our ear to vibrate 25,000 times. But we wouldn't be able to hear it. We would just know it's there because of the pain. So if anyone wants to, actually, I would advise against checking that because it does lead to a lot of pain. Okay, 6.1.5, detection and exploration. How can waves, again, 6.1.5 is also a triple only topic. How can waves be used for detection and exploration? So the differences in velocity, absorption, and reflection between different types of waves in solids and liquids can be used both for detection and exploration of structures which are hidden from direct observation. So let's go through a few examples to understand what that means. So ultrasound. Ultrasound waves have a frequency higher than the upper limit of hearing for humans. So that means anything that is bigger than 20,000 hertz. That is what we call ultrasound. Now, ultrasound waves are partially reflected when they meet a boundary between two different media. So if you've got air and glass or water, some of the ultrasound waves will bounce back. The time taken for the reflection to reach a detector can be used to determine how far away such a boundary is. So, for example, this allows ultrasound waves to be used for both medical and industrial imaging. So this will go into more detail as we work through. But let's give one quick example. Here's a boat, and here is a fish. It will release, that's a massive fish actually. Let me just make that a little more accurate. Here's that small fish represents a shoaler fish. So what happens now is the ultrasound moves down, is released from the ship, but when it hits the fish, it reflects right back. Now we know that, and what the ship can do is work out the distance from the fish to the ship. So we know to work out distance, it equals, um, so we know speed equals distance divided by time. So distance would equal speed times time. Now, in this case, we're talking about ultrasound, we're talking about sound. So what's the speed of sound? It's 330 meters per second. So we know it's going to be 330 multiplied by the time taken for the sound to hit the fish and come back to the boat. So let's say that was 6 seconds. So we now know distance equals 1,900 and, oh, I feel like I wrote that wrong. Yeah, 1,980 meters. But the time that we just calculated is the time that took to reach the fish and come back. We only want to know how far the fish is. So for that reason, we have to divide the distance by 2 because we only want to know the distance there. We've just worked out the distance to the fish and back again. So we have to divide that number by 2. So the distance is 990 meters. So another thing, how can waves be used for detection and exploration? Now, sorry, just before we move on, that can be used in medical as well. So that's how we can use ultrasound to find out what's in the womb of an expecting mother. If in some industries, it's also used to find weakness within metals or within walls, etc. So, for example, you've got a wall or a piece of metal, and you've got an area here that's got a crack. So, when the ultrasound goes through, you can find out where that crack is or where the damage is. Okay, seismic waves are produced by earthquakes. P waves are longitudinal seismic waves. They travel at different speeds through solids and liquids. So this image here, actually I'll explain it first and we'll talk through it. S waves cannot travel through a liquid. S waves are transverse waves. P waves and S waves provide evidence for the structure and size of the Earth's core. So as you can see here, S waves, well, we've got a liquid outer core. And because we've got a liquid outer core, that means the S waves can't go through because they're transverse. They won't go through the liquid. The P waves, however, can go through the liquid. Now, what that means is when you have an earthquake, all the P waves come out around this region here. And in this region here, you won't get any P waves, just S waves, because the S waves go through the liquid where they're refracted, and then they go through different liquid, solid, liquid, solid again. So you get S waves going the whole way through, and that helps understand where the epicenter was, where the earthquake occurred, but it also gives evidence of what's in the center, and it evidences the fact that there must be a liquid outer core and a solid inner core. Okay, so this is what I was just explaining before, echolocation or echo sounding. Using high frequency sound, the high frequency sound waves, it's used to detect objects in deep water and measure water depth. So same principle that I explained before. So here the the ultrasound's gonna hit the shoal fish and bounce right back. These bits, it'll hit the surface first and then bounce back. And the ultrasound here will hit the surface, bounce back. So they know this is the area where the shoal fish is. This is the place where they need to drop the net. Okay, 6.2.1. So this we're back to combined and triple topics. What are electromagnetic waves? So transverse waves, so let all electromagnetic waves are transverse. They're transverse waves that transfer energy from a source to the waves to an absorber. So any wave is the transfer of energy or information. Now, electromagnetic waves are grouped in the electromagnetic spectrum. It's a continuous spectrum, so that's something that needs to be remembered. It's a continuous spectrum of all the types of EM waves, and they travel at the same velocity through a vacuum or air. So they travel at, through vacuum or air, they travel at 3 times 10 to the power of 8 meters per second. So that's 300 million meters per second, or 300,000 kilometers per second. Now, you this end here, we've got radio waves, then we've got microwaves, infrared. In between infrared and ultraviolet, we have visible light, which is not mentioned in this here. Then we've got ultraviolet, X-rays, and gamma rays. Now, on the radio wave side, we've got long wavelengths. So as you can see, they've got large and long wavelengths. And as you go along, up to all the way up to gamma, the wavelengths become shorter and shorter. So gamma rays are very small. As you can see here, 10 to the minus 14 meters to 10 to the minus 18 meters. That's very, very small. Now, radio waves have a low frequency, so that means they've got less waves per second. And gamma rays, as you work your way across the electromagnetic spectrum, gamma rays have got very high frequency. Now, each wave carries a similar amount, same amount of energy. So you can appreciate then if you've got something that's got this many waves, well, the waves are that small, then and which means it's going to have a lot of waves in 1 meter. It's got high frequency, it's going to be carrying a lot of energy. So we have low energy here and high energy on this side. Okay, so really quickly, which element wave has the highest, which electromagnetic wave has the highest frequency? Gamma rays. And which electromagnetic wave has the high, oh, same question. Um, this question should say, what is the speed at which electromagnetic waves travel? And all the electromagnetic waves travel at the same speed through a vacuum, which is 3 times 10 to the power of 8 meters per second. Okay, refraction. Light refracts when it travels from one medium to another. That capital H there just means that it's a higher only topic. So light refracts when it travels from one medium to another. When light travels into a denser material, it slows down and bends towards the normal. So let's just look at that in a bit more detail. Imagine this is mud. Imagine this is the pavement. And you're walking with 3 friends. Now, when you're walking on the pavement, you're going to walk faster than when you're walking in the mud. It's really thick, gloopy mud, so it's going to slow you down massively. So we're all 3 friends are moving this way. But now this friend has entered the mud. So that friend starts to move slower. And because that friend's moving slower, now what we're also saying is the friends are holding hands. Now, because that friend's moving slower and the other two are moving faster, what happens? They get pulled inwards. So what's happened is their direction has changed. And which way has their direction changed? They've gone, they've moved inwards. So when you go from a place where you're moving faster to slower, it moves inwards. And that's what's happening here. When light refracts, it travels from one medium to another. When light travels into a denser material, so now let's use the same example. If it's going from air into water, so the light is traveling this way. When the light travels into a denser material, it slows down and bends towards the normal. So here's our normal at 90 degrees. Now the light should have continued this way, but instead it bends inwards. And that's happening because it's slowed down. And you can see that example better if you understand that if you're walking from a pavement into mud. Okay, so let's look at that same example now in reverse. So we're looking at when light travels in less dense material, it speeds up and it bends away. So this time, the 3 friends are in the mud and they're about to get back onto the pavement again. So they're walking in the mud. moving this direction. Now the first friend, oh sorry, I'm going to start that again. The first friend has entered onto the pavement, and that friend is moving faster than the rest. So he pulls them outwards. So now they've been pulled outwards. So they were moving in this direction, but now they're moving this direction. And same thing would happen if you're going from water to the air. So there's your initial ray of light in the water. There's the normal. So when light travels in a less dense material, it speeds up and bends away from the normal. So it'll bend away from the normal, like that. Again, so it's very important. The reason I've shown you the example using mud and pavement is just so you can understand what's happening. So refraction is the change of direction of a wave when it travels from one medium to another. Okay, so when light enters a glass, when light enters glass, it slows down and so it changes direction. So you can see here, it's bending inwards towards the normal. So it bends towards the normal. When light leaves the glass and enters the air, it speeds up and so it bends away from the normal. So with this kind of topic, it is possible to learn it just by understanding it, but it's still worth memorizing these key sentences. So it just makes it easy in the exam. But if you understand it, you can work it out. And that's always the best way. So again, this is something we covered before. Now, one thing to keep note of is the light that's entering. If you, and just in case you have to draw this yourself, the incident ray, now it says here light entering, but that's the incident ray. And this is the emergent ray. They have to be parallel. They're not going to be in line with each other, but they have to be parallel. So this is what we covered before. EM waves, they can transmit, in other words, go through something. So they can go through, for example, a window. They can be absorbed, and they can also be reflected. So all three things happen. Okay, so here's a quick question. It says, complete the diagram to show what happens to the ray of light when it comes out of the block. So we're going glass to air. We're showing it go from more dense to less dense. So it moves away from the normal. Explain why this happens to the ray of light. Because when it goes from the glass to the air, it speeds up. It starts moving faster. It travels at one speed in the glass, another speed in the air. It travels faster in the air, so it moves away from the normal. So the diagram shows two beakers. Both beakers have a drawing pin inside as shown. The first beaker is empty. The eye cannot see the drawing pin. The second beaker is full of water, and the eye can see the drawing pin. Explain how the eye is able to see the drawing pin in the second beaker. You may add a diagram if it helps you answer. So the difference here would be there's your light ray. When it goes from the water to the air, what happens? It bends away from the normal and goes towards the eye. So you need to show a straight ray from the pin to the water surface. Show the refraction going straight to the eye. Of course, you need to do that with a ruler and you need to draw a better normal than I have. Okay, properties of electromagnetic waves. How can we investigate the amount of infrared radiation radiated by different surfaces? So this is a Leslie cube, and the way the Leslie cube works is you add boiling water inside the Leslie cube. The Leslie cube itself has different surfaces: white surface, black, matte, and shiny. And there's a few different ways of doing this. You can use an infrared detector. That's the most accurate. And then you can measure how much infrared radiation is coming out of each one. And what that shows is how much each surface emits. Now, a surface can only emit if it absorbs. So usually emitting is a indicator of how well it absorbs as well. So white surfaces will emit less. Black surfaces will emit the most. Matte surfaces will also emit a lot of more infrared radiation. Shiny surfaces will emit less. That's because white and shiny are not good absorbers, they're better at reflecting. So if you think about a thermos that you put your hot tea in, it's usually a shiny silver surface, and that keeps the heat energy in because it reflects it. So how can we investigate the amount of infrared radiation radiated by different surfaces? So you place the Leslie cube on a heat-proof mat, fill the cube with very hot water, replace the lid, so it acts as an insulator and allow the heat energy to escape. Use an infrared detector to record the amount of radiation from each surface, and then construct a bar chart to display the results. So, how are electromagnetic waves actually generated? So, changes in atoms and the nuclei of atoms can result in electromagnetic waves being generated or absorbed over a wide frequency range. Gamma rays originate from changes in the nucleus of the atom. Now, what happens is this. Let's start with gamma radiation first. When you have an unstable nucleus, it will emit of some radiation. So it can either emit an alpha particle, a beta particle, or it can release energy in the form of gamma rays. So gamma rays come under radioactive, but also it's an electromagnetic wave as well. But it is essentially when that atom releases energy. Now, for other types of electromagnetic waves, for example, X-rays, ultraviolet rays, what happens is this. That is the atom and electron shells as well. The electron's on a lower energy level. Along comes some electromagnetic radiation and it is absorbed. When it's absorbed, that electron will move to a higher energy level. That electron eventually will give out that energy and then drop back down to its original energy level. The energy that it emits is an EM. So it might be X-ray, UV, infrared. So let me explain that one more time. The electron gains energy and goes to a higher energy shell. Eventually, it loses that energy and goes back down to its original place. And the energy that it emits, that energy is an EM radiation. Radio waves are generated slightly differently. Radio waves can be produced by oscillations in electrical circuits. So when radio waves are absorbed, they may create an alternating current with the same frequency as the radio wave itself. This means radio waves can themselves induce oscillations in electrical circuits. So what this means is when you've got your wire or when you've got your wire within an electrical circuit, what's flowing through that wire? You've got electrons flowing through it. Now, if they absorb energy, they'll start oscillating. Those oscillations, the movement of the electron, releases radio waves. So when that is done through a transmitter, it releases those radio waves with the same frequency as the electrons would have had. When that gets picked up, that radio wave energy is absorbed by electrons, and those electrons then oscillate with that same frequency as well, which then gets translated convert it into a sound, and then we hear that sound. So what are the risks of some of the parts of the electromagnetic spectrum? So again, very common question. It's actually it's commonly asked how electromagnetic waves are generated and also how radio waves are generated. But again, when you look through past paper practice, when you look at the mark schemes, these are the kind of mark schemes that I would advise that you memorize. So what are the risks of some of the parts of the electromagnetic spectrum? So you've got ultraviolet waves, X-rays and gamma rays are high in energy and they are ionizing radiation. Infrared, visible light, infrared, microwaves, radio waves, they're not really ionizing. So that means if the UV, X-ray, and gamma are ionizing, they can have hazardous effects on the human body tissue, as in they can cause bonds to be broken and leave what would look similar to a burn. Also, because they're more penetrating, they can cause that on the inside, so they can lead to things like cancer. Now, ultraviolet can lead to the skin aging prematurely, and it increases skin cancer risks. X-ray and gamma rays are very ionizing, very, very ionizing, and that can cause mutations of genes and cancer. So that means because they're penetrating as well, they don't really cause as much of an issue to the skin itself. What they cause an issue to, what they cause an issue to, what they cause an issue to is the actual bonds within the DNA. So in our cells, within our nucleus, the DNA, if it absorbs X-rays and gamma rays, it can cause the hydrogen bonds holding the DNA together to break apart and unravel. And then when that cell is replaced, it could be a cell that causes a mutation. So what does the harm caused by ionizing radiation depend on? So it could depend on the radiation dose, which is a measure of the risk of harm resulting from an exposure of the body to radiation. It's measured in sieverts. So the lower the dose, the lower the risk. The greater the dose, the greater the risk. The shorter the wavelength of the radiation, the more ionizing it is, and the greater the risk. So you've got gamma rays, which are very short wavelength, X-rays, very short wavelength. That means they're carrying more energy. This means that gamma rays are more harmful than X-rays, and it will cause more damage to tissue. But what we usually deal with in hospitals, or if anyone's had X-rays, etc., what you're dealing with in hospitals is low dose, and you're dealing with things with short half-lives. And because you've got short half-lives, that means they're not in our system for as long. With X-rays, the dose is quite short, but quite a small dose, and there's lots of protective equipment around as well. Okay, some of the properties of infrared and microwaves are the same. State two of these properties. So infrared and microwaves, they travel at the same speed. They're both transverse. They can be reflected, refracted, absorbed, travel through a vacuum. Any of those will give you the 2 marks. So that's been answered there. Um, we've put the question there twice because it comes up a lot. Now, give one possible danger of exposing your skin to ultraviolet radiation, skin cancer, and aging skin. Complete the sentence. X-rays can be dangerous to people because X-rays are ionizing radiation. What happens when a metal aerial absorbs radio waves? It creates an alternating current with the same frequency as the radio waves. Also, it gets hotter because you've got more oscillations occurring. You have an increase in resistance. Okay, uses of electromagnetic radiation. So radio waves, are used in television and radio. So radio waves are transmitted easily through the air. They can be reflected to change their direction easily. They do not cause damage if absorbed by human bodies, and that makes them ideal for safe use. Microwaves you can use for satellite communication and cooking food. So this is high frequency microwaves have a frequency which are easily absorbed by molecules in food. Now we say molecules, it's more the water within food. Water absorbs the microwaves. So in other words, to the temperature, because it's absorbing this energy, the microwave energy, the water heats up and it cooks the food around it. So it conducts. That heat energy is conducted into the food around it and it cooks it and it cooks the food. They pass through the atmosphere, so it's great for communication. So most of our mobile phones run off microwaves. Infrared. We use it for electrical heaters, cooking, food, infrared cameras. Infrared light has frequencies which are absorbed by chemical bonds. So infrared light has frequencies which are absorbed by chemical bonds. Now, if it's absorbed by chemical bonds, this increases the molecule's internal energy and causes heating. So, if, for example, you've got a piece of food, the chemical bonds within the food absorb infrared radiation, and that causes the bonds to break and reform in a different format. In other words, they denature proteins. Um, as one example, all objects emit infrared light, and so they're also useful for detecting objects in the dark. Visible light, so fiber optic communications is an example of that. Visible light can be transmitted and reflected, which means that coded pulses of light can be used in fiber optic communications. We, of course, also use it to see things. You can use it in cameras. So it's quite diverse. So ultraviolet is using energy efficient lamps. And it can be used in sun tanning. It can be used to spot fake money as well in banks. UV also increases the pigment melanin in the skin, causing tanning. So melanin increases in the skin which is the same as tanning. However, there are risks of this. So the more people use UV radiation for tanning, uh, it increases the risk of skin cancer. X-rays and gamma rays can be used for medical imaging and also treatment. So not only can they cause cancer, they can treat cancer too. They're both transmitted through body tissues. So that means if the issue is internal, it can go through the skin and go to the internal organs with very little absorption. They both don't really get absorbed too much by the skin. So they're both transmitted through body tissue with very little absorption. So it goes through our skin, fat layers, etc., making them ideal for imaging and treatments. So it's easy then to get an image of the internal structure. Also, it's good for treatments because you can send the X-ray and gamma rays to the parts of the body where the cancer might be. So name one more type. So microwaves and visible light can be used for communication. Name another type of electromagnetic wave that can be used for communication. You can say infrared or radio waves. Which of the electromagnetic waves is given out by a TV remote control? Infrared, but you can use radio waves there as well. Now, what property of the wave in your answer above makes it suitable for satellite communications? The fact that they can pass through the atmosphere. So, more than infrared, the answer would have been radio waves. Because radio waves, and because infrared, so radio waves and microwaves are able to go through the atmosphere better. Okay, describe the properties of X-rays which enable it to be used to photograph bone structure. So X-rays pass through the flesh, in other words, the skin, etc., and but they're absorbed by the bone. Okay, in as much detail explain how microwaves heat up food. So they're absorbed by the water, and then the hot water heats up the food. Name two types of electromagnetic waves that can be used for communication. So we've got microwaves, radio waves, infrared, visible light. Okay, 6.2.5 is a topic which is triple only. So how do lenses work? The distance from the lens to the principal focus is called the focal length. So there's the principal focus, I think where all the rays join together, and there's the lens. So that's the focal length. So in a convex lens, parallel rays of light are brought to focus in the principal focus. So that's a convex lens then. What it does is it bends the light inwards. So convex uh, lens bends the light inwards. Concave bends the light outwards. And these are symbols that you can use. Now, convex can make a real or virtual image, and concave can only make a virtual image. So let's understand each one in a bit more detail. So a real image is formed when the rays of light actually meet at a point. So if you look back here, all these rays of light are meeting at a point. When they meet at a point, then it's a real image. So for example, whatever's coming from there, that's going through this convex lens, you can project it onto a screen, like in a cinema or on a wall. So for example, a projector shines a real image onto a screen. In a camera, the image formed on the sensor or the film is real. Now, how do we know it's a real image? Um, the light rays come together. So here the rays of light are focused that can be projected onto a screen. They can always be seen on a screen. So these 2 points are mentioned here. And they're always inverted. So what you see initially is upside down. Now it's in a virtual image. A virtual image is formed when light rays appear to meet, but don't actually meet. So for example, when you're looking in the mirror, you look into a mirror like this. Now, according to this, the light rays are meeting here. That's why you can see it. But actually, the light rays don't meet there. So that shows that it's a virtual image. So a virtual image is formed when the light rays appear to meet, but don't actually meet. You can't project it onto a screen, but you can see it with your eyes. So examples are looking at itself in a mirror, looking at something through a magnifying glass. So in this case, the light rays don't actually meet. The light rays don't meet, the light rays can't be projected, and you always see the image upright or magnified. So this is a quick kind of summary of it all. In a real image, the rays meet. In a virtual image, they don't. They appear to, but they don't. Real image can be seen on a screen. Virtual image can't. Examples, a projector or a camera. A virtual image example is a mirror or a magnifying glass. Now, in a real image, usually it's inverted or flipped. Because when they meet at a point, when they go beyond that point, the light rays they go opposite directions. As in the light rays flip, because they meet at that point there, and beyond that point, you end up with a flipped image. Now, with virtual image is usually an upright image. Okay, so what's the difference between a convex and a concave? So a convex lens is thicker in the middle, like this. than it is at the edges. Parallel light rays that enter the lens converge, meaning when parallel light rays go through it, they refract inwards. And so they converge and they meet at a point. The point that they meet at is what we call the principal focus. A concave lens is thinner in the middle than at its edges. This causes parallel rays to diverge, meaning they refract outwards. They separate, but they appear to come from a principal focus on the other side of the lens. So, because the rays of light are going outwards like this, you have to track them back. They end up meeting, so the rays of light actually meet before the lens. So the principal focus is before the lens. So that usually leads to a virtual image. Okay, and how can we calculate magnification? So this is similar to what we learned in biology. When we use a magnifier, when we use a microscope, magnification equals the image height divided by the object height. So you can use I, image equals the object height, which is the actual height, times the magnification. So you can use I equals am. Okay, so visible light can be specular or diffuse. Now, if you've got a smooth surface, all the rays of light bounce off in the same direction. So you get a specular reflection. You get to see the image. So when you're looking in a mirror, what you see is a specular reflection. When you look at, for example, a piece of paper, you've got a rough surface. So you get diffuse reflection. That's why you can't see your own image in when you look into look at a piece of paper. Now, the white light, if it goes through a triangular prism, what happens to it? The white light breaks apart into all the different colors that it's made up of, which are the colors of the rainbow, which you can see here. Now, if you add a blue filter, what happens is all the colors are absorbed by the blue filter, but it allows the blue light to transmit through. And this is why we see colors. So if you're looking at something, if if we're looking, for example, this is a purple color. What that means is when white lights hit it, all these colors have been absorbed, but this one color here has been reflected. Why can we see this red colored pen, the one that I've drawn a blue arrow towards, or that blue arrow? Because it's absorbed every color, but the color that's reflected from it is the red. So what determines the color of an opaque object? Which is what I just said. The color of an opaque object is determined by which wavelengths of light are more strongly reflected. So for example, this t-shirt is strongly reflecting orange light, whereas all the other colors are not reflected, they're absorbed. This one's white, so that means it reflects all the colors. When all the colors are reflected, then it would appear white. With black, it means all the range of colors are absorbed. Now, what determines objects that transmit light are either transparent or translucent. So, for example, when drinking water, orange juice or lemonade, for example, which is quite light in color, you can just about see through it just slightly, and that's because it is slightly translucent. Whereas our windows in our house are transparent. What are the poles of a magnet? The places in a magnet where the magnetic forces are strongest. So you can see here, the magnetic field always goes from north to south. Where you've got more lines together, that's where the magnetic field is strongest. As they get further and further apart, then the magnetic field gets weaker and weaker. So the place in the magnet where the magnetic force is strongest is where you've got more magnetic field lines. So two like poles repel each other, and um, two opposite opposing poles will attract each other. Now, when two magnets are brought close together, they exert a force on each other, a non-contact force. So you can either get attraction or repulsion. So here's your repulsion, and if you had north and south, then you would have attraction. Okay, so we've got two different types of magnets, a permanent magnet or an induced magnet. Induced magnetism always causes a force of attraction. So when removed from the magnetic field, an induced magnet loses most, if not all, of its magnetism quickly. Permanent magnets do not lose their magnetism. So if it's induced, it means it's only temporarily a magnet at that point. So a permanent magnet, a material that produces its own magnetic field. Induced magnet, a material that becomes a magnet when it's placed in a magnetic field. So for example, if I have a magnet like this, that's permanent. It has a permanent magnetic field. If I attach a paper clip here, it temporarily turns that paper clip into a magnet. And because it's temporarily turned into a magnet, I can add another paper clip there, which turns this temporarily into a magnet. Another paper clip here, which temporarily turns that into a paper magnet. Into a temporary, it turns it into a induced magnet, sorry. So our permanent magnet here turns this paperclip into induced magnet, turns this one into induced magnet, this one into induced magnet. And then I can add another paperclip and it'll turn to an induced magnet until the gravitational pull is bigger than the force of attraction from the magnet. Then the paperclips fall. Now, if I remove this magnet, if I remove the magnet, what's going to happen? Then all these paper clips collapse. There's now that they are no longer within a magnetic field, they're not induced magnets anymore. So they would all collapse, they would all fall down, and they would be no longer magnetic. Okay, so quick, nice simple question here. Explain what is meant by the following statement. A non-contact force acts on each magnet. So it means the magnets are not touching, but they still experience a force. So what is a magnetic field? So the strength of the magnetic field depends on the distance from the magnet. The direction of the magnetic field at any point is given by the direction of the force that would act on another north pole placed in that point. The direction of the magnetic field line is from north pole to the south pole of the magnet. So what we're saying is this part of the magnet is the strongest part. Um, that's the strongest part because you can see that there's more magnetic field lines. This part's the strongest part. But as you get further and further away, you start to see these bigger gaps forming between each field line. You can see it between this line, and this line. The gaps are getting bigger and bigger. As the gaps get bigger and bigger, it means the magnetic field is getting weaker and weaker. Now, a magnetic compass contains a small bar magnet. So you have a small bar magnet inside. Now, alongside that, the Earth already has a magnetic field as well. So the compass needle points in the direction of the Earth's magnetic field. The behavior of the compass proves the Earth has a magnetic field. So when you're using a compass, it has um, a small bar magnet. Now, that bar magnet will be affected by a magnetic field. So if I got a magnet, a permanent magnet, and put it here, I can get that small bar magnet inside to spin using this permanent bar magnet. Now, because the magnetic field of this permanent bar magnet will have an effect on that small magnetic field. However, the Earth also has a magnetic field. So the Earth's magnetic field would also have an impact on the magnet. Okay, so how can we plot a magnetic field of a magnet? So this can sometimes come up. Place the magnet on a piece of paper and draw around it. So first things first, draw around the magnet. Mark the north and the south poles. Place the compass by the point of the magnet. So for example, you might put it here, and then you put a little dot. Make a dot at the tip of the compass needle, just there. Now you move the compass where the dot was, and wherever the arrow is pointing, you put a dot there. Then you put your compass in the next place, and wherever the arrow is pointing, you put a dot. Again, whichever way the compass is pointing, make a dot. And you keep doing that until you've got all these little dots. When you move all the compasses, you just join all the dots together, and that shows you a magnetic field line. So as it says here, we draw a line through all the dots and add an arrow to show the direction of the field line. And then repeat for different starting positions. So you do it again here, you do it here, for as many field lines as you can draw. Okay, so this is a nice breakdown of how we would do that. Describe how to plot the magnetic field pattern of a bar magnet. So number one, place a plotting compass near the north south pole of the magnet and mark the direction that the compass points. Then move the plotting compass around the bar magnet to your other pole, marking at regular intervals the direction the compass points. Join all the points up and add an arrow pointing from the north pole to the south pole. So exactly what we just went through on the previous 3 slides. Okay, now we get to the fun part of this topic. So I'll read out what it says, but then I'll explain it in my own words. So when a current flows through a conducting wire, a magnetic field is produced around the wire. The strength of the magnetic field depends on the current through the wire and the distance from the wire. So, on one way we know which way the current is flowing is by using our right hand, as is shown in that picture, and the curvature of the hand, so that if you grab hold of the wire, the curvature of the hand shows the direction of the magnetic field, and the thumb shows the direction of the current. So, what we need to understand here is that when a current flows through a conducting wire, so here we've got a current flowing through a conducting wire. When we say current, what do we actually mean? We mean the flow of electrons. So we've got electrons flowing through. When current flows through an electric wire, it automatically produces a magnetic field. And the magnetic field, you know which way it's going based if you use this right-hand rule. So let's break that down a little bit. Current is the flow of electric charge or electrons through a wire. Now, when current flows, it creates a magnetic field around the wire, which we've just shown. Now, that's an invisible field that can affect magnets or other current-carrying wires nearby. So, if you look at how the magnetic field has been formed, it's formed concentric circles, a bit like the ripples in a pond. Now, what we need to know here is what's going to affect the strength. of this magnet. So if we increase the current flowing through, so in other words, you increase the voltage, and we increase the current, what's going to happen? We're going to have a stronger magnetic field. Also, the further you get away from this magnetic field, the weaker the magnetic field gets. The same way in a magnet. Okay, this is a solenoid. So again, I'll explain this in my own words after we read through it. Now, if you shape a wire to form a solenoid, it increases the strength of the magnetic field created by a current through the wire. I'm going to explain what that means in a second. The magnetic field inside a solenoid is strong and uniform. I'll explain that too. The magnetic field around a solenoid has a similar shape to that of a bar magnet. So if you look at the way we just saw the bar magnet before, you can see here straight away that the magnetic field strength is exactly the same. As in the magnetic field is similar as you would get in a bar magnet. If you add an iron core in the middle of it, it increases the strength of the magnetic field of the solenoid. So first here, let's understand what a solenoid actually is. So literally what all a solenoid is a long coil of wire, and it's coiled up like a spring. So it's made by wrapping the wire into loops. That's all a solenoid is. First things first, that's all a solenoid is. It's a coil of wire. Now, why would we shape the wire into a solenoid? Why put it into these loops? As in, why convert the solenoid into these loops? That's because if you just have current passing through a straight wire, it creates a magnetic field, but it's actually quite weak and it spreads out. So the magnetic field, it dissipates in a sense. But when you coil it up, when you coil the wire up, this happens. As you can see in the picture, the magnetic field becomes stronger and more focused because now that the strongest part of the magnetic field is now within the coils. So it's not being lost. Now, so that means the magnetic field becomes stronger and more focused. Now, stronger magnetic fields, each time you add a loop to this magnetic field, as in the solenoid, every time you add a loop, what happens? It makes the magnetic field stronger. Also, if you look inside it, the magnetic field is uniform. So inside the solenoid, the magnetic field lines are straight, they're parallel, they're close together. So that means inside there, that's a really strong magnet. So that means because it's uniform, it means the field strength, the magnetic field strength is strong and it's the same the whole way through. Now, so the magnetic field, this is what we've already just covered here. The magnetic field around the solenoid is just like the magnetic field around a bar magnet. So you have a north, you've got a south. The field lines loop from one end to the other, except the lines in the middle, which are uniform, parallel, straight, close together. So what we're actually saying here is that the solenoid actually behaves like a magnet. So as soon as you turn the electricity on around that set of wires, what does that set of wires turn into? It turns into a magnet. So we'd call this an electromagnet. And if you want to make this stronger, you add a iron core, or you can add a permanent magnet. But an iron core will do the job. Iron core is better because magnetism is induced inside the iron core. Because it's induced, when the current turns off, the magnetism stops inside the iron core. So then you can use something like this to pick up. So let's say you've got a trash can full of iron and lots of other types of metals. You get this coil of wires, turn the electricity on, and it will act like a magnet and it will attract all the iron, all the magnetic material. Then once it's attracted, rather than pulling it off, you just turn the electricity off, turn off the current, and it stops being a magnet because it only has a magnetic field when the electricity is flowing through it. So that means we can use this kind of technology because this essentially is an electromagnet. We can use it for cranes, magnetic locks, So at school, you've got those, I don't know if you've got them in your school, but you might have them in your school, magnetic locks. Most schools have them now, electric bells, MRI scanners, all of this uses solenoids. Okay, so let's have a quick look at this question. The student gives the steel ball bearing a gentle push in the direction of the iron rod. At the same time, the student closes switch S. Explain the effect on the motion of the ball bearing when the switch S is closed. So now switch S has been closed, we've got a complete circuit. Now, once electricity flows through this wire, now what do we call this wire? This coil of wire? We call it a solenoid. So what's going to be formed in that solenoid? It's going to have a magnetic field. So which is what we just said. So it causes a current in the coil. So that turns this coil of wire into a solenoid. A magnetic field is created. So now, and they've added an iron rod there to make it a stronger electromagnet. Now we have an attraction between the steel ball bearing, because steel has a magnetic material inside it, iron. Steel is made of iron. So as long as it's iron, cobalt, nickel, it can be attracted by the solenoid. So the steel contains iron, so the iron is attracted by that solenoid. So the force of attraction acts on the ball bearing, so the ball accelerates. It accelerates towards a solenoid. Okay. Okay, Fleming's left-hand rule. So again, I'll read through it, then I'll explain it. So what we're looking at here is the motor effect. When a conductor carrying a current is placed in a magnetic field, the magnet producing the field and the conductor exert a force on each other. So what we're saying here is when you have something creating a magnetic field and something causing a current, um, then what that does, they exert a force on each other that causes the movement of something else. So when a conductor carrying a current is placed in a magnetic field, the magnetic the magnet producing the field and the conductor, the current, the one that has a current flowing through it, exert a force on each other, and that causes the conductor to move. So Fleming's left-hand rule represents the relative orientation of the force, the current, and the conductor, and in the conductor and the magnetic field. So what this means is with your left hand, if you put them at perpendicular to each other, all three fingers, the thumb shows the direction you're going to have movement. Your first finger shows north to south movement, as in the magnetic field, and your second finger shows the direction the current flows. Now, a really good way to remember this is FBI. First finger is F, which is the motion, the force. Second finger is B, which, as you'll see from this here, B is magnetic flux density. So that's the magnetic field. And I, as we already know, is current. Now, let's go through this in a bit more detail. Fleming's left-hand rule, what it actually helps you do is predict the direction of the force, direction of the motion on the wire carrying current inside the magnetic field. So imagine you've got two magnets, north here and south here. In between here, you've got a magnetic field going that way. And now in between, I put a wire, and the wire has a current flowing this way. So now, if you have a magnetic field and you've got a conductor, which is the wire carrying a current, we have got we've got B and we've got I. So if we put our fingers pointing in the right direction, we will know which way the wire is going to move. So this time for ease, let me just erase this. Let me do it going the other way. So we've got, in this case, if we use our left hand, Our first finger is pointing from north to south, left to right. We have our second finger pointing in our direction. So which way is our thumb pointing? Our thumb is pointing upwards. That means in this scenario, the wire would move upwards. And this is what we mean when we say Fleming's left-hand rule helps us to predict the direction of force on a wire carrying current inside a magnetic field. So when does it apply? It applies when you have a current flowing through a conductor. So the first thing we've got is we've got that metal wire. It's a conductor, we've got current flowing through it. And that conductor has been placed inside a magnetic field. So it's in between these two magnets. And when you've got two magnets close to each other, you have a uniform magnetic field there. Now a force is produced and the wire moves. So these three things go hand in hand. Force, that movement is caused by the magnetic field and the current interacting with each other. Now that's the basic principle behind how an electric motor works. Remember, a motor moves to make other things move. And why is that motor moving? Because it has a magnetic field and it has electricity flowing through a conductor. So now, in Fleming's left-hand rule, we've got our thumb, our first finger, our second finger, all the right angles, they're all at right angles, they're all perpendicular to each other. So you can see that here. Right angle, right angle. And we know our FPI to help us understand it better. Okay, I hope that has helped make a lot more sense out of it. Now we need to memorize this formula. Well, we don't need to memorize the formula, but we do need to memorize the units. So newtons, meters, because you could be given a question where it's just got lots and lots of stuff linked to centimeters or millimeters. And current is in amperes, and this is a new one. Magnetic flux density is measured in Tesla. But this is not the type of Tesla that needs boycotting. Okay, so let's move on now. Let's actually look at how an electric motor works. So again, I'll read through it and then I'll explain it in my own words. A simple electric motor can be built using a coil of wire that's free to rotate. So look, a simple electric motor can be built using a coil of wire. So a coil of wire is our conductor that will have current flowing through it, and it's free to rotate between two opposite magnetic poles. So here's our magnetic pole here and magnetic pole here. Now, when electricity flows through this coil of wire, this wire, the coil experiences a force and it moves. In other words, it starts to spin. A device that has a coil of wire carrying a magnetic field so electric motor is a device that has a coil of wire carrying a magnetic field that tends to rotate. So you can imagine here, this side here, you've got, if we look at first finger, our first finger is pointing this way. Our current is going this way. So that means our thumb is pointing upwards. So this half of this motor is going to rotate upwards. On the other side, the current's flowing the opposite direction. So that means our north to south is still the same. Our current is going this way. So our thumb is going to point downwards. So this half is spinning downwards. So in other words, it's spinning. And if it's spinning, that kinetic energy can cause other things to move. You can attach a wheel to it, it'll make the wheel move. So again, let's go through this one more time. So how does an electric motor work? So the electric motor, if you think about this, what's flowing through that wire? It's electrical energy. And what's it doing with that electrical energy? It is converting it into kinetic energy. So let's go through that one step at a time. So simple motor, as we know, it's got a coil of wire that has a current flowing through it. It's got it's got your north and south pole magnets. It's got a power supply. It's got a battery, and it's got a commutator. So this is your commutator. The commutator just helps it spin, as it allows it to freely spin. But you don't need to know too much detail about the commutator. Now, what happens when current flows? The coil carries the electrical current, as we can see. Let me just highlight it. Actually, in fact, let me just remove my bits of drawing first. So the coil carries electric current. The coil is sitting in a magnetic field, which is going north to south. So you can see how that coil is in the magnetic field. So now, as soon as you have an interaction between the magnetic field and the current in the coil, what happens? It creates a force. So it causes this wire to move. And specifically, it causes this half to move downwards and this half to move upwards. That's the bit that we need to understand. And that causes it to spin in circles. And I've explained that from a Fleming's left-hand rule perspective as well. Okay, so let's move on. Okay, now 7.2.4 till the end of this presentation is triple only. So if anyone's doing combined, this is a point where you can log off now. And the rest of this booklet, the rest of this presentation is triple, purely triple. Now, loudspeakers gets covered now, and microphone comes afterwards. So, loudspeakers and headphones use the motor effect to convert variations in current in electrical circuits to the pressure variations in sound waves. So, what that means is the current in the electrical circuit is varying and passes through a coil. The coil experiences the force. The varying current causes the coil to vibrate. The coil causes the cone to vibrate, and the vibrating cone causes air molecules to move. Now, that's what you need to know, but that's not always the easiest thing to understand. So let's go through this in a bit more detail. Because this uses electromagnets and it uses the motor effect. So let's look at this step by step. Now, the varying current, because it says here, the current in the electrical circuit is varying and passes through a coil. Okay, so if you've got a coil and it's got current flowing through it, then what's going to be produced around it? A magnetic field. So a varying current flows through the coil. So the electric signals that produce the varying current come from the music or from someone's voice. They're not constant. When someone's speaking, the electrical signal becomes stronger. When someone's silent, you don't have as much of a electrical signal. These signals pass through the coil of wire inside the speaker. So you've got your coil of wire and you've got electrical current flowing through it. Now the coil sits within a magnetic field. So north, south. So whenever the current flows, the motor effect kicks in. Now, what we're saying here is that when the electrons flow through, what we're now getting is the motor effect. So that means that that spring, so that solenoid or that coil of wires are going to move. So that means the magnetic field and the current interact, and it produces a force on the coil. So you can work out which way the force is moving using Fleming's left-hand rule. Now the direction and the strength of the force is the important bit. Because the current is varying, the force coming from that coil is constantly changing as well. They're moving back and forth. That makes the coil vibrate back and forth very quickly. Now the vibrating coil is linked to a speaker cone. So the coil is attached to a cone, which is like a thin, flexible material. And as the coil vibrates back and forth, it makes the cone move in and out as well. And so because this cone is moving in and out as well, what's the cone going to do? It's going to vibrate air particles. And when it causes vibration in the air particles, it pushes and pulls those air molecules, and that creates longitudinal sound waves. And then we hear the sound. So that way, then our ears detect that change in the air vibrations and we detect it as sound. So let's just do that let's summarize what I've just said. We vary the current. So the current's flowing through this in various amounts. So that means the electricity, the electrons flow through this solenoid, through this coil of wire. Okay, and that's happening inside the magnetic field. So that means the current, that coil has a current, it has a magnetic field. When the magnetic field and the current interact, what happens? We get movement, we get motion. So that means this wire, based on the current flowing through it, it's going to move back and forth. When it's got lots of electrical current flowing through it, it's going to move back and forth faster. When it's got less, it's not going to move as much. That coil that's moving is attached to a cone. When this cone, which is like the skin of a drum, it's moving back and forth. It produces a sound, and then that sound is released as longitudinal waves, and our ears detect it. So I hope that makes sense. Any questions, please ask. So, how does the generator effect work? In fact, just at this point, just a quick point I want to make. I hope everyone can see that if you understand that motor effect, it opens up the whole topic. You've got to just understand the interaction between magnets and the coil that's got current flowing through it. If you understand the interaction between the conductor or the metal wire carrying the current and the magnet, this whole topic becomes so much easier. It just opens up the whole topic. Okay, so if an electrical conductor um, moves relative to a magnetic field, so if an electrical conductor moves relative to a magnetic field, or if there's a charge in the magnetic field around a conductor, a potential difference is induced across the ends of the conductor. So if the conductor is part of a complete circuit, a current is induced in the conductor. Right, so let's understand what this means. So the generator effect is what we're looking at now, is how we produce electricity using movement and magnetism. So what we're saying is when a wire moves through a magnetic field, in fact, you know what? Let's go through the example of this first. So an example of this is a real life example of a generator effect is a wind turbine. So imagine this thing, the slip rings here, overall, they're attached to a wind turbine. Now, when that wind turbine spins, what's it going to spin? It's going to spin that coil. So, from Fleming's left-hand rule perspective, what we've now got is we've got motion, because we've got the thumb. We've got it, we're moving it ourselves with the windmill, with the wind turbine. We've got a magnetic field, and so our second finger current is going to be produced. If we have two, we automatically get the third. That's what this whole section's saying. So when a wire moves through a magnetic field, or when a magnetic field changes around a wire, it produces a potential difference. In other words, it starts to create current on one side but not the other side. So you get a difference in potential. Potential difference. That potential difference then pushes the electrons through. So if the wire is part of a complete circuit, the potential difference, as you can see, this is a complete circuit. The potential difference makes the current flow through it. So in other words, it produces electricity. This is how we generate electricity. So for example, we can use wind turbines, bike dynamos, all these things use the same principle. What we're going back to here is Fleming's left-hand rule. You've got three things here. Force, you've got magnetic field, and you have current. Now, what we were looking at initially is that if you've got number two and number three, as in you've got magnetic field and current, it produces number one. But when we're talking about the generator effect, we're saying if you've got number one and you've got number two, it creates number three. In other words, it creates electricity. So let's look at this step by step. A wire or a coil is moved through a magnetic field, or the magnetic field near a wire is changed, i.e. by moving the magnet. So you could spin the magnet instead and just keep the wire in one place if you wanted to. It would have the same effect. This motion, what does it cause? A potential difference across the ends of the wire. So we say voltage has been induced. If voltage has been induced, what does voltage do to the electrons in the wire? It gives them a push. So if the wire is connected in a closed circuit, the voltage makes the current flow. And now what's happened? Electricity has been generated. And that's it. So like in a wind turbine, the blades spin. Look what it does. It spins the coil that's in that magnetic field. So it's in this case, it's this coil that's spinning within the magnetic field. Similar thing in bike dynamos, similar thing in a power station. So an induced current generates a magnetic field that opposes the original change, either the movement of the conductor or the change in magnetic field. So that's just, I've explained that in my own words. I know that with a lot of PowerPoints, a lot of the stuff that you may have covered in school, it really covers this topic in a really complicated way. When in reality, it is it's a difficult topic. Don't get me wrong, but if you understand the principle, you only had to actually understand the first two or three slides, and everything else fits in with that same thing. Okay, so now what we're looking at is what affects the direction of the induced potential difference or current. So the direction of the induced potential difference it depends on two things. The direction of movement. So if you move the wire or magnet in the opposite direction, the induced current also reverses. So this is something we've actually already covered. It's just that if you spin it, if you spin it upwards, as in your thumb is facing upwards and your magnetic field is going from this side to this side, then the current is going to be coming out towards you. If you spin it downwards, so your thumb's going that way, the magnetic field is still left to right, then the current is going to go in towards the screen. Essentially, that's all this is saying. And you can either change the direction you're spinning the coils, or you could change that, you can turn that into a south and turn that into a north. That will change the direction the current is formed. So depending on which way you spin it, or which way your north to south is, the current's going to be formed in different directions. And what affects the size of the induced potential difference or current? And that can be changed by increasing the speed of the movement. so you can spin this faster. You can increase the number of turns of the coil. So that wire has coils, you can increase the number of coils on it, or you can increase the magnetic field strength. All of those will have a knock-on effect on the overall strength. Now, what is our solar system? So within our solar system, there's one star, the sun, plus 8 planets, the dwarf planets, and that orbit the sun. So all of these things in our solar system orbit the sun. We've got natural satellites, we've got the moons. The moon is a natural satellite that orbits planets, and they also make up the solar system. Our solar system is a small part of the Milky Way galaxy. So if you take all the different solar systems, the solar system is all the different things that orbit a star. So our star, which we call the sun, is orbited by planets and moons and dwarf planets and some other things, but it's a small part of the Milky Way galaxy. Now the sun was formed from a cloud of dust and gas pulled together by the gravitational attraction of all these particles. Now, initially, if you have anything that has mass, has a gravitational pull. So initially in the life cycle of the star, what would have happened is you would have had all these particles coming towards each other, and gravity would have pulled them all towards each other. Now, if you had a large mass of particles, then small masses of particles would have combined with them as well. The gravity would have pulled them in. So they would have orbited until eventually being taken in. Now, what that meant initially would have been the gravity would have been so strong that it would have been it would have taken up quite a small space. Because the gravity of the kind of mass that you have for a star, the mass is so much that the gravity would have been so strong that it would have crushed everything together. But now what you've got is so many particles and you've got lots and lots of friction. And that friction would have caused heat energy. And that heat energy would have meant it would have started to cause some sparks of light. So just small sparks of light within there. And overall, eventually there would have been so much energy that that energy would have provided enough energy for fusion to occur. So fusion, and I'll show this really simply, it's more complicated than this, it's where two hydrogen nuclei combine. So this is two hydrogen nuclei combined to make helium. But it goes beyond that. Helium can then combine with hydrogen to make another element. Two heliums can combine. So hydrogen and helium can combine to make lithium. Two heliums can combine to make boron, beryllium, and so on and so on. Until it goes up to, I think, iron. Beyond that, there needs to be, the star would have to explode to make anything heavier than that. Now, what that meant was gravity was pulling everything inwards, and it would have been quite a small. The mass would have been very heavy, but it would have used a small space because the gravity would have been so strong. So the gravity makes the sun contract inwards, but the force that's released due to the fusion reactions pushes in the opposite direction. And hence we get what we call the sun. This is why we get this size here. The sun that we see in the sky, the reason it's that big is because of the balance between these two forces. So there's also a force due to the radiation pressure, which is making the sun expand. So one, gravity is pulling it inwards, and the fusion reaction and the radiation that's occurring within the sun is pushing it outwards. So how does a star remain stable? A star goes through a life cycle. The life cycle is determined by the size of the star. So the fusion process in stars produce all of the naturally occurring elements, as I've just shown on the slide before, but elements heavier than iron are produced only in a supernova. Only a supernova would provide enough energy to fuse them together. So the explosion of massive stars, supernova, distributes elements throughout the universe. Now we have a medium-sized star, so that wouldn't necessarily supernova. It would only be a giant star that supernovas. And when it does supernova, it explodes and it sends elements everywhere. So how does a star remain stable? So the hydrogen fuel has been used up. It's being used up. So this is what will happen after the stable phase. So at the moment we are in a stable phase. Our star is in a stable phase for another billion years or so, potentially. The hydrogen fuel is now, as soon as the hydrogen fuel is used up, in other words, you only have heavier elements now, its temperature will decrease, but its luminosity increases. It will change to a red giant. Is Now at that point, when it becomes a red giant, its temperature will increase and its luminosity will start decreasing. Sorry. So when the hydrogen fuel is used up, when the hydrogen fuel is used up, the temperature decreases, but luminosity increases. At that point, it's a red giant. Then the temperature starts increasing and the luminosity decreases. At that point, it becomes a white dwarf. It's just a really good question to memorize. At different points in their life cycle, stars change from one group to another. Describe what will happen to the sun between it leaving the main sequence group and it becoming a white dwarf. So describe what happens to the sun between it leaving the main sequence group and becoming a white dwarf. So essentially what we just went through. So sun goes from main sequence to red giant, then it goes from red giant to white dwarf. When the sun changes to a red giant, the surface temperature decreases, but its luminosity increases. When it changes from red giant to white dwarf, the surface temperature increases, but the relative luminosity decreases. So exactly what we went through on this slide. Okay, the universe now contains a large variety of different elements. Describe how this happened. So fusion takes place in stars. Hydrogen formed into helium. The fusion continued, so that even within our star, the fusion will continue and form larger elements. Elements heavier than iron are only formed within the supernova. Elements and then elements are scattered by the supernova explosion throughout the universe. Okay, some stars are much more massive than the sun. So we've not gone through this, but this question answer, the 6-mark question, brings everything together. Describe the life cycle of stars that are much more massive than the sun, including the formation of new elements. So fusion processes in the star produce new elements. Cloud of gas, hydrogen, and dust or nebulas. So fusion produces new elements. So initially there would have been a cloud of gas. So what we're saying is describe the life cycle of stars much more massive than the sun. So initially there would have been a cloud of gas, hydrogen, or dust, or nebula. They all got pulled together due to gravity. This is what I was showing initially. Now that causes an increase in temperature. And that starts the fusion process. So this is what I went through in that first slide. And that's what we call a protostar. Now in that protostar, we now have enough energy for fusion to occur. In other words, hydrogen nuclei fuse to make helium nuclei. And the star becomes main sequence. When it becomes main sequence, the hydrogen gets used up to converting into helium, so it starts to run out. The helium nuclei fuse to make even heavier elements all the way up to iron. The star expands to become a red supergiant. The star collapses rapidly and explodes, and we call that a supernova, creating elements heavier than iron and distributing them throughout the universe, leaving behind a neutron star or a black hole. So a neutron star is one that spins rapidly, releasing only small amounts of light, or a black hole, which is essentially all that matter. Now, there's no fusion reaction happening, so all that matter just has high levels of gravity. So it's just pulling everything inward. Okay, the sun is at a stable stage of its life. Explain in terms of the forces acting on the sun what this means. So the sun is subject to two balancing forces. The force of gravity, which makes it contract, and a force due to temperature, heat, energy, radiation, pressure that makes it expand. Now, what causes that pressure or that heat or that temperature, that energy is the fusion reaction. Okay, orbital motion. How do objects maintain circular orbits? So gravity provides the force that allows planets and satellites to maintain their circular orbits. So gravity provides the force that allows planets and satellites to maintain their circular orbits. So for an object to remain in a steady circular orbit around an object, it needs to be going at the right speed. Now, just a few things to keep in mind here. When something goes round in a circle, if something's moving around in a circle, it has a centripetal force. That force, keep in mind, force equals mass times acceleration. So every time we exert a force on something, it leads to it accelerating. Now, in this case, for example, the moon goes around the Earth or the Earth goes around the sun, there's a force thing acting on it, so therefore it's accelerating. But if we were to look at its speed, which is a scalar uh, quantity, its speed remains constant, but its direction is constantly changing. So it has its speed stays the same, but its direction keeps changing, meaning its speed stays the same, but the velocity is constantly changing. If the velocity is constantly changing, then it means whatever is orbiting something else is accelerating. Now, if something is closer to the source of the gravity, because that force of gravity is bigger. So, for example, if I move something closer to a magnet, then the magnetic field is going to be stronger. If you move something closer to the Earth, the force of the pull from gravity, the force is going to be stronger. That means if force is stronger, the acceleration will be bigger. If you move something further away, it's further away from that pull of gravity. So that means the acceleration will be smaller. So that the overall velocity of it will be smaller as well. And what I've just said there explains the next few slides. So for an object to remain in a steady circular orbit around an object, it needs to be going at the right speed. This is because an object orbiting another maintains its orbit if there's a balance between its velocity and the gravitational pull of the object it's orbiting. So for circular orbits, the force of gravity can lead to changing velocity, but unchanged speed. So the speed stays the same, but it's changing velocity because the direction keeps changing. The force of gravity causes the satellite to accelerate because force equals mass times acceleration. So force causes acceleration. The acceleration causes a change in direction. Acceleration is a change in velocity. So if we accelerate something, we change its speed. Not its speed, we change its velocity, sorry. So the change of it, the speed doesn't change, but what changes? The velocity changes because the direction changes. The speed does not. Now, the gravitational attraction between two objects decreases with distance. This means the closer two objects are to each other, the stronger the force of gravity between them. So if the force between them is greater, the greater acceleration will occur. The greater the acceleration, the greater the change in velocity. So in other words, if something is closer, it has a stronger force acting on it. The gravity will be stronger, the force acting will be stronger. If the force is bigger, the acceleration will be bigger, which means the velocity will be bigger. So it'll be changing direction more often. Objects in small orbits travel faster than objects in large orbits. In order to change orbital speed, an object must change the radius of its orbit at the same time to maintain a stable orbit. So if something wants to slow down, it needs to exert a force outwards so it can increase its orbital speed. So it can move further away, and the further it moves away, the slower its overall orbit will become. Okay, redshift. What is our evidence for the Big Bang theory? Now, further evidence for the Big Bang is the presence of cosmic background radiation. So it is believed that the remains of radiation produced shortly after the Big Bang, which is now thinly spread across the whole universe. So the thought process is at the time of the Big Bang, the Big Bang created so much radiation that it's now spread throughout the universe. So we have this background radiation all the time. So if you think back to the radioactivity topic, the background radiation is this. The cosmic background radiation is from the Big Bang. Okay, now what evidence do we have for the Big Bang theory? There's an observed increase in the wavelength of light from most distant galaxies. Now, the further away the galaxy is, the faster they're moving and the bigger the observed increase in wavelength. This effect is called the redshift. So the observed redshift provides evidence that space itself is expanding and supports Big Bang theory. Now, essentially what it's saying is, if something is moving away from us, then when you look at its wavelength, particularly if you look at the wavelength of the microwaves, they are longer than expected. It's like they've been stretched. And if something is moving towards us, that's called a blue shift, they've noticed that the waves become smaller. So the way you can look at this is if you're stood here and your friend is stood there and you're holding a slinky and your friend starts running away from you, what happens to the slinky? It stretches. And that's what's happening here. Because these other galaxies are moving away from us, the radiation that they're emitting is also stretching because as they're releasing it, they're moving at the same time. So one way you could look at it is when, for example, if you have a police car, when the police car drives past you, that noise it makes, that's the stretching of the sound wave. So it's using that thought process. So what essentially it's showing is that galaxies are moving away from us, and if majority of galaxies are moving away from us, it shows that the universe must be expanding. So it also supports the Big Bang theory. That's from the point the Big Bang happened, the universe has expanded and expanded and expanded. A good question for a scientist would be, what is it expanding into? But that's got nothing to do with your GCSE exam, but still a good question to think about. Okay, galaxies show a red shift. So this is our evidence. But more distant galaxies show a bigger redshift. That suggests galaxies are moving away, the fact that galaxies are moving away from us suggests that the universe is expanding. More distant galaxies are moving away faster. So the universe, therefore, must have been in one place at one point, and then from that point onwards, everything has expanded away. Okay, now there's still a lot about the universe that is not fully understood. For example, dark mass and dark energy. Now, let's start with dark energy. So dark energy is an unknown form of energy that is thought to cause the universe to expand faster and faster. So in simple terms, scientists have discovered that the universe is expanding. And it's not just steadily, it's accelerating the expansion. So there must be something causing this push, but they don't know what it is. So they call that mysterious push, or that thing, whatever's pushing it to become bigger and bigger, they call that dark energy. So they don't know what it is. They have no evidence of it 100%. They just know there must be something there that's causing it to continue its expansion. So they call it dark energy. Then we've got dark matter. So dark matter is an unidentified form of matter that would explain why some galaxies are spinning faster than we'd expect them to spin. Now, in simple terms, galaxies are spinning so fast that in reality they're spinning so fast that they should be flying apart, but they don't. Because the gravities, they have such strong gravities that everything stays held together. That suggests is that there must be an additional invisible mass. Potentially, there must be something that holds it together with gravity. So that invisible mass that they're not sure exists or not, they call dark matter. Now we can't see it, but we can assume it's there because of the gravitational effects. So what that means is dark energy is speeding up the expansion of the universe, and dark matter adds the extra gravity to galaxies to stop them from flying all over the place. Okay, some really good exam practice here that I would advise that you have afterwards, if you're watching this video, that I would advise you pause on and work your way through. And well done, we have reached the end of Physics Paper 2. Okay, now we're going to continue with Biology Topic 7. This is the last part of Biology Topic 7, and this is triple award. So 7.4 and 7.5 are purely triple award, and this is the last part that we'll finish. And that by finishing this, we'll have finished all of the biology topic paper 2 content as well. So as we already know, plants and algae produce their own food. They are producers. So that is trophic level 1. Then trophic level 2 are the herbivores that eat the plants and algae. They're known as primary consumers. Trophic level 3 is the carnivores that eat herbivores. They're the secondary consumers. And finally, we have our fourth level, which is carnivores that eat other carnivores or herbivores, and they're known as tertiary consumers. Now, as you can see, as you go up through this process, the energy level decreases. Now, here it says, even with producers don't take in much of the sun's energy. But if we say that's 100% energy, the primary consumers will only retain about 10% of their energy, 10% of the energy, because they lose some of their energy through excretion, movement. A lot of the energy is used up. And then you've got your secondary consumer, which again loses 90%. So 90% is lost at each stage. And then you've got your tertiary consumer, which loses another 90%. And energy is lost through excretion and movement predominantly, and growth as well. That means if someone was to eat a tertiary consumer, it would, from an energy perspective, it wouldn't provide much energy. So it's herbivores that provide the main energy supply, which is why we eat, generally speaking, people eat chickens, cows, goats, lambs, sheep. So trophic level 1 are the producers, trophic level 2 are the primary consumers, trophic level 3 are secondary consumers, and trophic level 4 are the tertiary consumers. Now, the decomposers help break down dead plants and animals. They achieve this by releasing enzymes into the surroundings, and then small soluble food molecules then spread into the microorganism. So they'll release the enzymes, and once the enzymes break down the food into like a liquid, then those organisms are able to absorb that liquid. In other words, in a sense, it osmoses back into them. Now, biomass pyramids can be created to show the relative amount of biomass at each level of a food chain. Biomass meaning how much matter they're made up of. So level 1, we always have the most amount of mass. So biomass pyramids can be created to show the relative amount of biomass at each level of a food chain. Producers, mainly plants and algae, convert approximately 1% of incoming light energy into energy for photosynthesis. So like I said, most of the light energy doesn't get absorbed. There's not enough plant life in the world to absorb all of it. So trophic level 1 is at the bottom of the pyramid. That's the one that has the most energy. Only about 10% gets passed on. Now, losses of biomass are due to not all ingested materials absorbed. So the caterpillar will eat the tree, but not a lot of it will still be released as feces. Some absorbed materials are lost as waste, like carbon dioxide and water during respiration. And water is also lost in urine. Water and urea is lost in the urine. So how can the efficiency of biomass between trophic levels be calculated? You calculate the difference between the biomass between two trophic levels and divide it by the biomass input. So you can do this for energy to calculate the efficiency too. For example, if we said 100 here and this is 10, from level 1 to level 2, we've lost 90. So, because it says biomass input, biomass output, so there's a 90 output. 90 has been lost. So it'd be 100 take away 90 divided by the original, which is 100. So that would equal 10 divided by 100, 10%. Okay, now what is food security? Having enough food to feed a population. So that could be done through increasing birth rates. Now, food security can be affected by the cost of agricultural inputs. So actually to increase agriculture, it can cost more money. There's new pests and pathogens which can cause an issue in food security. Now, environmental changes can impact food production, leading to issues like famine in some countries if there's a lack of rain. So, food production efficiency can be enhanced by minimizing the energy loss from food animals to the environment. So, like we said before, what's the main two ways of using up energy? And the main two ways are by movement and excretion, also growth. So, how can you increase the size of the animal? You can restrict the movement of the animal and regulate the temperature of the environment, meaning they don't have to respire as much and use up their fat reserves. And certain animals are given high protein foods to promote growth. So it's massively cruel, but it does increase the food output. So what this farming techniques, the advantages of certain farming techniques leads to fast food production. It uses less space and it's cheaper for farmers. So doing this kind of thing, it produces more food. It uses up less space because you've got these chickens cooped up into one small section each. But it leads to poor animal welfare. Disease spreads easily. So if one gets ill, they're all next to each other. And it is a cruel treatment. Sustainable fisheries. So fish stocks in the ocean are declining. So we need to maintain fish stock at a level where breeding continues, otherwise species may disappear. Fish is one of the most eaten proteins around the world, and it's so easy to catch if you've got a big ship or a couple of big ships with nets. So, how can we conserve fish stocks? One is with fishing quotas, so that limits the number of fish caught so stocks can recover. And the other one is net size limits. So they can, what that means is you have nets with quite reasonable sized holes, so smaller fish can escape and grow. And that also helps keep populations stable. So one of the things they now have done is when people catch certain types of fish or lobster, etc., around the world, they have to measure it first. Also, they have to look at it and see if it's pregnant or not. So if they find a pregnant fish or a pregnant lobster, etc., they would throw that back into the water. So they are some well, there are now some companies that are doing things in a sustainable manner. Now, biotechnology has helped meet the demands of growing human population as well, because we can use genetic modification or genetically modified crops, crops that have had their genes changed and are known as genetically modified crops. This might involve crops that can withstand insects or herbicides. So that means a farmer will get a better yield or a better harvest because less will have been eaten by insects, and it means they can use herbicides without killing off the plant. So genetically modified crops have increased yields in general. Now, bacterial cells have made genetically engineered, and bacterial cells have been genetically engineered to make useful substances such as human insulin to treat diabetes. So it's been used in that manner as well. So things like fungus fusarium is used for making mycoprotein. So this is a protein-rich food suitable for vegetarians. The fungus is grown on glucose syrup. Oops, sorry. It's grown on glucose syrup in aerobic conditions. Now, when we say it's grown on glucose syrup, that means it's providing with glucose. Aerobic conditions provide it with plenty of oxygen. So it can do lots of respiration and grow quite a lot. And the biomass is then harvested and purified. So these are ways of then decreasing. I mean, long term, this is a positive because it means you can slowly try to decrease the reliance upon animals, which means the less need for deforestation. Okay, well done, everyone. That is the end of AMALathon 2. That's the end of the biology topic. We've now completed all of biology, chemistry, and physics. So well done for getting to the end. If you have any questions, you can contact us via the website, the YouTube channel, or the WhatsApp channel as well.